What if everything you thought you knew about the universe was only the beginning? Picture a reality where time isn't constant but fluid, where the very fabric of space can ripple like water, and where black holes don't just consume matter, they rewrite the rules of existence itself. These aren't scenes from science fiction. They're real phenomena being uncovered right now at the frontier of astrophysics, challenging our most fundamental understanding of reality. For centuries, we've looked up at the stars with wonder, but today we're peering deeper than ever before into the cosmos's most guarded secrets, and what we're finding is more astonishing than anyone could have imagined. Welcome to the Chronicles of the Universe, where we embark on an extraordinary journey through the latest groundbreaking research in space-time phenomena. In this video, we're going to explore how gravitational waves allow us to hear the collision of black holes billions of light years away, how dark energy is silently tearing the cosmos apart at an accelerating rate, and how the very nature of time and space might be far stranger than our everyday experience suggests. This is cutting-edge science supported by observatories like LIGO, the Event Horizon Telescope, and the James Webb Space Telescope, institutions that are fundamentally reshaping our cosmic perspective. Each discovery doesn't just add a new piece to the puzzle, it challenges us to rethink the entire picture of existence, from the smallest quantum fluctuations to the vast expanse of the multiverse. You're about to witness a narrative that stretches from the birth of the universe to the farthest reaches of theoretical physics, a story filled with enigmatic forces, invisible matter, and possibilities that border on the magical, yet are undeniably real. This journey will not only expand your mind but might also leave you with a profound sense of connection to the cosmos and our place within it. So settle in, open your curiosity, and prepare to see the universe in a completely new light. What you discover here today won't just inform you, it will transform how you perceive reality itself. Picture the sheer scale of this detection. Two black holes, each roughly 30 times the mass of our Sun, locked in a final, fatal dance over 1 billion light-years away. Their immense gravity warps the space around them, and as they spiral inward at a fraction of the speed of light, they set the very fabric of reality ringing like a struck bell. This is the event that the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured on September 14, 2015, a whisper from the distant cosmos that confirmed a prediction Albert Einstein made a century prior. The technology that made this possible is a masterpiece of precision. LIGO 2 observatories, separated by nearly 2,000 miles in Louisiana and Washington, each feature two 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down these vacuum tubes, bouncing off mirrors suspended at the ends. In normal circumstances, the light waves return and cancel each other out. But when a gravitational wave passes through Earth, it minutely stretches space in one direction and compresses it in the other, changing the length of the arms by a distance 10,000 times smaller than the nucleus of an atom. This tiny shift creates a flicker in the laser light, a signal that something monumental has occurred. This first detection wasn't a solitary event. It was the opening of an entirely new field of astronomy. Before this, our view of the universe was limited to the electromagnetic spectrum, light, radio waves, X-rays. But gravitational waves are a completely different messenger, allowing us to perceive the universe through the medium of space-time itself. We are no longer just stargazers, we are now listeners, tuning into the cosmic symphony of some of the most energetic events in existence. The sources of these waves are as varied as they are violent. Binary systems, where two dense remnants like neutron stars or black holes orbit each other, are prime producers, their inevitable mergers sending out powerful chirps that LIGO and its European counterpart, Virgo, can detect. Even the catastrophic collapse of a massive star into a supernova can, in theory, generate a detectable burst of gravitational waves if the explosion is asymmetrical, though such a signal has yet to be conclusively identified. Each type of event writes its own unique signature in the data, telling scientists about the masses, spins, and distances of the objects involved. Perhaps the most transformative moment in this new era came in August 2017, with the detection of an event known as GW 170817. This was the collision of two neutron stars, and for the first time, gravitational wave observatories alerted traditional telescopes to turn and look. What they witnessed was a kilonova, a spectacular explosion that forged and scattered heavy elements like gold, platinum, and uranium across space. In one observation, we learned that the gold in a wedding ring or the uranium in a power plant was likely created in such a cataclysmic event billions of years ago. This single event brilliantly connected the physics of gravity with the physics of atomic nuclei, providing a tangible origin story for the elements that make up our world and even our own bodies. By mapping the origins and strengths of these waves, astronomers are beginning to chart the distribution of the most massive objects in the universe, building a gravity-based map of the cosmos that complements our light-based one. This is how we listen to the universe's deepest secrets, not with our eyes, but by feeling the subtle vibrations of spacetime itself. Now, let's shift our gaze from the ripples in spacetime to an even more profound and enigmatic force that permeates the very void between galaxies. For much of the 20th century, astronomers believed they understood the ultimate fate of the cosmos. After the Big Bang, the universe was expanding, but the collective gravitational pull of all matter, stars, galaxies, dark matter, was thought to be acting like a cosmic brake, gradually slowing this expansion. The great debate was whether there was enough matter to eventually halt and reverse the expansion in a big crunch, or if the universe would simply coast onward, forever expanding but at a steadily decreasing rate. Then, in the late 1990s, two independent teams studying distant supernova made a discovery so shocking it would win them the Nobel Prize and upend cosmology itself. They found that the universe isn't slowing down at all, it's speeding up. The expansion is accelerating, driven by something invisible and utterly mysterious, dark energy. This revelation came from observing Type 1a supernova, which are the spectacular explosions of white dwarf stars. These events are what astronomers call standard candles. They have a known, consistent intrinsic brightness. By measuring how bright they appear from Earth, scientists can calculate their distance with remarkable accuracy. Furthermore, by analyzing the redshift of their light, they can determine how much the universe has stretched since the explosion occurred. The teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, expected to see that the most distant supernova, whose light has been traveling to us for billions of years, would appear brighter than expected because the expansion was slower in the past. Instead, they found these ancient stellar explosions were fainter. This could only mean one thing: the space between us and those supernova had stretched more than anyone had predicted. The expansion of the universe was accelerating. It was as if you threw a ball into the air, and instead of falling back down, it shot away from you faster and faster into the sky. The entity causing this acceleration, dark energy, is now understood to constitute about 68% of the entire mass-energy content of the universe. This makes it the dominant component of reality, yet we have no idea what it actually is. the leading explanation harkens back to an idea Albert Einstein himself proposed and then later discarded: the cosmological constant. He introduced this term into his equations of general relativity to allow for a static universe, a notion that was the prevailing view at the time. When Edwin Hubble later discovered the universe was indeed expanding, Einstein called the cosmological constant his greatest blunder. But modern physics has resurrected the idea in a new form. In quantum theory, empty space is not truly empty. It is a seething foam of virtual particles constantly popping in and out of existence. This quantum vacuum is believed to possess an inherent energy density, and this energy, this pressure inherent to space itself, could be the source of dark energy's repulsive gravity, pushing the universe apart. However, this elegant idea runs into a colossal problem. The vacuum energy calculated by physicists is astronomically larger by a factor of 10 to the power of 120 than the value observed for dark energy. This is arguably the worst theoretical prediction in the entire history of science, a discrepancy so vast it suggests our understanding of the quantum vacuum or gravity is fundamentally flawed. This has led to other, more exotic theories. Perhaps dark energy isn't a constant but a dynamic field that has changed over the life of the universe, an idea sometimes called quintessence. Or perhaps our theory of gravity itself, Einstein's general relativity, breaks down on the very largest scales and needs to be modified. To unravel this mystery, cosmologists are undertaking monumental surveys of the sky. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope and Vera-C Rubin Observatory are meticulously mapping the positions and shapes of billions of galaxies across cosmic time. They are looking for subtle clues in how large-scale structure forms. The gravitational pull of dark matter tries to clump galaxies together, while the repulsive push of dark energy works to smooth everything out. By measuring the rate at which cosmic structures grow and the precise distances to faraway objects, these surveys aim to measure the strength and constancy of dark energy's push, hoping to distinguish between a true cosmological constant and a dynamic field. The implications of dark energy are not just academic, they speak to the ultimate fate of everything. If dark energy is indeed a constant force, as the cosmological constant suggests, the universe will continue on its current path. Galaxies outside our local group will eventually be pushed away so far and so fast that their light will no longer be able to reach us. The observable universe will shrink to a small island of galaxies, and the rest of the cosmos will fade into eternal blackness, leading to a cold, isolated end known as the Big Freeze or heat death. But if dark energy is something stranger and stronger, if it intensifies over time, a far more dramatic finale awaits. In this Big Rip scenario, the accelerating expansion would eventually overcome all forces holding things together. First, galaxy clusters would be torn apart, then individual galaxies. With space expanding faster and faster, the gravitational bonds holding stars within galaxies would snap. In the final moments, planetary systems would be ripped apart, and finally, atoms, molecules, and even the very fabric of space-time would be shredded. The discovery of dark energy forces us to confront these profound possibilities, reminding us that we live in a universe whose deepest workings are still largely unknown, and whose future is written in a language we are only just beginning to decipher. But if the concept of an event horizon boggles the mind, the nature of what lies at its center is perhaps the ultimate mystery in physics. This is the singularity, a point of infinite density where the known laws of physics simply break down. Here, spacetime is curved to an extreme degree by an unimaginable concentration of mass, and our understanding of gravity, as described by Einstein's general relativity, reaches its mathematical limits. It's a realm where the classical world of stars and planets gives way to the bizarre, probabilistic domain of quantum mechanics, and the greatest challenge for modern theoretical physics is to find a theory of quantum gravity that can describe what truly happens in this most extreme of environments. This quest to understand the singularity is not just an academic exercise. It forces us to confront the fundamental nature of reality, space, and time itself. Our understanding of these cosmic monsters was utterly transformed by the work of Stephen Hawking, who made a startling theoretical discovery in the 1970s. By applying quantum theory to the edge of a black hole, Hawking realized that these objects are not the perfect, eternal traps they were once thought to be. The intense gravitational field just outside the event horizon can spontaneously create pairs of virtual particles from the energy of space itself. Normally, these particle pairs would instantly annihilate each other and return their energy to the vacuum. But at the precipice of a black hole, one particle might fall in while the other escapes into space. To an outside observer, this stream of escaping particles looks like a faint glow of thermal radiation, now famously known as Hawking radiation. This process means that black holes are not completely black. They have a temperature, and they slowly, over trillions upon trillions of years, lose mass and energy, eventually evaporating away entirely. This brilliant insight was the first major step in bridging the chasm between the world of the very large, governed by gravity, and the world of the very small, ruled by quantum mechanics. Black holes are not a one-size-fits-all phenomenon. They come in a staggering range of scales. The most common are stellar mass black holes, the remnants of massive stars that have exhausted their nuclear fuel and collapsed under their own immense weight in a supernova explosion. These can be a few times to several dozen times the mass of our Sun. Then there are the intermediate mass black holes, which are more elusive but are thought to form from the mergers of smaller black holes or the collapse of massive gas clouds in dense star clusters. At the pinnacle of cosmic structure reside the supermassive black holes, behemoths weighing millions or even billions of solar masses. These giants lurk at the very heart of nearly every large galaxy, including our own Milky Way, which hosts a relatively quiet one named Sagittarius, a star. The origin of these supermassive objects is a topic of intense research. Did they grow from smaller, seed black holes that accumulated mass over time? Or did they form directly from the collapse of enormous clouds of primordial gas in the early universe? Their existence is deeply intertwined with the evolution of the galaxies they anchor, as the energy released from matter falling into them can regulate star formation and shape the entire galactic ecosystem. This brings us to one of the most profound and enduring puzzles in modern physics, the black hole information paradox. According to the principles of quantum mechanics, information about the state of a physical system can never be truly destroyed. It might be scrambled beyond recognition, but it is always preserved in some form. However, if an object falls into a black hole, it seems to be lost forever behind the event horizon. And if the black hole then evaporates via Hawking radiation, which is purely thermal and contains no information about what fell in, then that information appears to have been erased from the universe, violating a fundamental tenet of quantum theory. Stephen Hawking himself initially believed this information was lost, sparking a decades-long debate. A potential resolution comes from the holographic principle, which suggests that all the information about everything that falls into a black hole is not lost inside but is instead encoded on its two-dimensional event horizon, much like a hologram stores three-dimensional information on a two-dimensional surface. The fate of this information remains an active and fiery frontier of theoretical research. The recent detections by LIGO and Virgo of gravitational waves from merging black holes have provided a powerful new tool to test our theories about these objects in the most extreme conditions imaginable. By carefully analyzing the chirp signal of a merger, the increasing frequency and amplitude of the waves as the black holes spiral inward, scientists can infer the masses and spins of the objects involved. These observations have already delivered surprises, such as the discovery of black holes with masses that were not thought to be common, challenging our models of stellar evolution. Each collision is a natural laboratory for testing the predictions of general relativity in regimes of incredibly strong gravity, and so far, Einstein's theory has passed every test with flying colors. The data from these cosmic crashes are like echoes from the edge of spacetime, providing direct observational clues about the nature of gravity and the behavior of matter under conditions we could never hope to recreate on Earth. Yet for all their theoretical elegance, these cosmic shortcuts come with a list of formidable challenges that currently consign them to the realm of mathematics and imagination. The most immediate problem is stability. The moment a wormhole forms, calculations show it would likely pinch off and collapse into a black hole faster than even a single photon could traverse it, instantly severing the connection. To prop it open, you would need a truly bizarre form of material threading the tunnel, something physicists call exotic matter. This isn't just unusual stuff. It's matter that possesses negative energy density or negative pressure, effectively generating a form of anti-gravity that pushes against the wormhole's natural tendency to crush itself. While certain quantum effects, like the Casimir effect, demonstrate that negative energy densities can exist in tiny amounts in a lab, the scale required to stabilize a wormhole large enough for a person, let alone a spaceship, is astronomical, far beyond any technology we can even conceive of. Furthermore, there's the issue of quantum instability. The intense, fluctuating energies at the heart of a wormhole would likely cause it to be wildly unpredictable, potentially collapsing violently or behaving in ways that make it utterly impassable. These are not mere engineering hurdles. They are fundamental physical barriers that suggest nature might actively prevent the creation of such shortcuts to preserve causality and prevent the logical paradoxes they could unleash. This brings us to the most mind-bending implication of wormholes: their intimate connection to time travel and the potential to unravel causality itself. Because general relativity treats space and time as a single, flexible entity, a space-time tunnel doesn't just connect two places, it could also connect two times. If one end of a traversable wormhole were taken on a journey at near light speed or placed in a strong gravitational field, time dilation would cause that end to age more slowly than the stationary end. Upon returning, the two mouths of the wormhole would be out of sync, creating a bridge not just between locations, but between two different moments in time. Step through one way and you might emerge in the past, step through the other and you jump into the future. This scenario immediately invokes famous paradoxes like the grandfather paradox, where a time traveler could prevent their own existence. Physics has various proposals to resolve these, such as the Novikov self-consistency principle, which suggests that any actions taken in the past were always a part of history and cannot change it, or the many worlds interpretation, where any change creates a branching parallel universe. Yet, the very fact that our equations allow for these possibilities forces us to confront deep questions about the fundamental nature of time and whether the universe has mechanisms to prevent such logical inconsistencies from ever occurring. Perhaps the most profound modern development in wormhole physics is its unexpected and revolutionary link to the quantum world, specifically through the phenomenon of entanglement. This connection was crystallized in a groundbreaking proposal known as ER=EPR, put forward by physicists Juan Maldacena and Leonard Susskind. The idea suggests that the mysterious, instantaneous connection between two entangled particles, what Einstein called spooky action at a distance, might be physically mediated by a microscopic wormhole. In this view, the particles aren't communicating faster than light. They are essentially two ends of the same tiny bridge in spacetime. This doesn't allow for sending information or matter, but it provides a stunning geometric picture of quantum connectivity. It implies that the fabric of spacetime itself might be woven from an underlying network of quantum entanglement, with these microscopic wormholes serving as the stitches. This is more than just a poetic analogy. It's an active area of research in string theory and holography, offering a potential pathway to finally unifying the laws of gravity with the laws of quantum mechanics. In this bold vision, the largest structures in the cosmos and the smallest particles might be connected through the most elusive tunnels in reality. Now, let's expand our perspective from a single universe to a breathtakingly vast cosmic landscape. Imagine not just one cosmos, but an infinite tapestry of them, each with its own unique history, physical laws, and perhaps even alien forms of life and consciousness. This is the multiverse hypothesis, a concept that pushes the boundaries of reality itself, suggesting that everything we can observe is merely a tiny bubble in a frothing sea of universes. The idea doesn't come from wild speculation but emerges naturally from our most successful scientific theories, particularly cosmic inflation and string theory. Inflation, the period of exponential expansion right after the Big Bang, doesn't necessarily stop everywhere at once. According to models proposed by physicists like Andre Linde, it can be eternal, continuously spawning new pocket universes in a process called eternal inflation. Each of these bubbles could have cooled differently, resulting in a random roll of the dice for the fundamental constants of nature: the strength of gravity, the mass of an electron, the power of the nuclear forces. In most of these universes, the numbers might not allow for atoms to form, or stars to ignite, or life to emerge, but in a rare few like our own, the conditions are just right. This offers a potential explanation for one of the most profound mysteries in science, the fine-tuning problem. Why do the fundamental constants seem so exquisitely calibrated to allow for our existence? The multiverse answer is a statistical one. If there are enough universes, it becomes inevitable that at least one will have the winning ticket. We shouldn't be surprised to find ourselves in a universe that permits life, because we couldn't exist in any of the others. To bring some order to this dizzying concept, physicist Max Tegmark has proposed a fascinating classification system, organizing multiverses into 4 distinct levels. Level 1 is perhaps the easiest to grasp. It's simply a continuation of our own observable universe. Due to the finite speed of light, we can only see a sphere of space about 93 billion light-years across. But if the entire cosmos is infinite, then somewhere far beyond our horizon, there are regions of space where every possible arrangement of particles is replicated. This means there could be an identical copy of you reading an identical copy of this script on an identical Earth somewhere inconceivably far away. Level 2 introduces the idea of bubble universes from eternal inflation, where each pocket has not only different initial conditions but potentially different physical constants. This is where the laws of physics themselves might change from one bubble to the next. Level 3 arises from the many worlds interpretation of quantum mechanics proposed by Hugh Everett. In this view, every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits, branching off into a near infinite number of parallel timelines where every possibility is realized. In one branch, a radioactive atom decayed. In another, it did not. This isn't science fiction fantasy, but a serious, albeit controversial, attempt to resolve the strange measurement problem in quantum physics. Finally, Tegmark's Level 4 is the most radical, the ultimate multiverse composed of all possible mathematical structures. Here, universes aren't just governed by different physical laws. They are built on entirely different mathematical foundations, existing in realms of reality so alien we cannot even begin to imagine them. Of course, such a grand idea faces intense criticism, primarily centered on its testability. If these other universes are forever beyond our reach, causally disconnected from our own, can the multiverse truly be considered a scientific theory? Critics argue it risks becoming a metaphysical speculation, an untestable article of faith that explains everything and therefore predicts nothing. Proponents counter that while we may never visit another universe, we might find its fingerprints in our own. For instance, if our universe collided with another bubble universe in the distant past, it could have left a detectable imprint in the cosmic microwave background, a kind of cosmic bruise on the sky. Some scientists have even searched for such signatures in the Planck satellite data, though no conclusive evidence has been found. Others suggest that the mysterious dark flow, the apparent coordinated motion of galaxy clusters, could be the gravitational tug of a neighboring universe. Furthermore, the many worlds interpretation makes specific, testable predictions about quantum probabilities that differ from other interpretations. While definitive proof remains elusive, the search itself is driving new technological and theoretical innovations, pushing the boundaries of how we define and do science. The multiverse concept forces us to ask fundamental questions about the nature of reality and our place within it. If we are just one universe among countless others, it can feel humbling, even diminishing. But it can also be seen as empowering. It suggests that our universe, with all its beauty, complexity, and life, is part of a grander, more extravagant reality than we ever dreamed possible. But this strange stretching of time isn't just a theoretical curiosity. It's a real-world effect that must be accounted for every single day to make modern life function. The Global Positioning System, or GPS, is a perfect example of relativity in action, a network of satellites that would become uselessly inaccurate within minutes if not for our understanding of time dilation. Each GPS satellite orbits about 12,500 miles above the Earth, moving at nearly 8,700 miles per hour, according to special relativity, because these satellites are in rapid motion relative to observers on the ground. The atomic clocks on board should tick slower due to velocity-time dilation. Calculations show this effect would cause the satellite's clocks to fall behind ours by about 7 millionths of a second per day. However, general relativity introduces a counteracting effect. The satellites are also higher up in Earth's gravitational well, where space-time is less curved. In this weaker gravitational field, clocks actually run faster than they do on the surface. This gravitational time dilation is a stronger effect, causing the satellite's clocks to gain about 45 millionths of a second per day. The net result is that the clocks on the satellites gain roughly 38 millionths of a second each day compared to clocks on Earth. This might seem infinitesimally small, but because GPS relies on ultra-precise timing signals traveling at the speed of light to calculate position, an error of even a few millionths of a second translates to a positioning error of hundreds of meters. If engineers did not deliberately build this correction into the system, your phone's navigation would be off by about 6 miles a day and would quickly become completely worthless. Every time you use your phone to find a coffee shop or navigate a road trip, you are personally and practically benefiting from Einstein's revolutionary insight that time is not absolute. To push this concept to its most extreme imaginable limit, we need to look at the most powerful gravitational fields in the universe, black holes. The gravitational time dilation near a black hole is so profound it creates what seems like a magical, or perhaps terrifying, visual paradox. Imagine an intrepid astronaut whom we'll call Alex on a mission to study a black hole firsthand. From the safety of your spaceship a safe distance away, you watch as Alex approaches the event horizon, the point of no return. As Alex gets closer to this boundary, you would see something bizarre happen. Their spaceship would appear to slow down, almost as if caught in cosmic glue. The light reflecting off their ship would become increasingly redshifted, stretching into longer and longer wavelengths, shifting from visible light to infrared and then to radio waves, making the ship fade from view. From your perspective, Alex would never actually cross the event horizon. Instead, they would appear to freeze there, their image becoming eternally stuck and dimmed into invisibility as time stretches to a complete halt relative to you. Yet from Alex's perspective, something entirely different occurs. They would feel no sudden jolt or barrier at the event horizon. They would cross it smoothly and continue their journey inward, all within a finite amount of their own personal time. This disconnect isn't an illusion, it's a fundamental feature of how gravity warps reality. The flow of time itself for Alex is radically different from the flow of time for you, the distant observer. This extreme example forces us to abandon the comforting Newtonian idea of a single, universal clock ticking away for everyone. There is no now that applies to the entire universe. Instead, time is a personal experience, woven into the very fabric of space-time and dependent entirely on your state of motion and your local gravitational environment. This leads us to a much deeper question that physicists and philosophers continue to grapple with. What is the nature of time itself? Is it a fundamental property of the universe, or is it, as Einstein himself sometimes speculated, merely a persistent illusion? The phenomenon of time dilation suggests that time is not a separate, invisible river flowing at the same rate for all, but is intrinsically linked to the three dimensions of space, creating a four-dimensional spacetime continuum that can be warped and curved. Our everyday perception of time as a linear, relentless forward march might be a kind of local artifact, a consequence of our particular perspective within this continuum. The laws of physics, for the most part, are symmetric in time. They work just as well if you run the equations forward or backward. This stands in stark contrast to our daily experience, where we remember the past and anticipate the future, where eggs scramble but never spontaneously unscramble. This apparent directionality, known as the arrow of time, is thought to arise from the statistical tendency of the universe to move from order to disorder, a concept called entropy. Yet relativity shows us that the rate at which this disorder unfolds is not fixed, it is elastic. The closer we get to understanding time, the more it seems to dissolve into a complex relationship within the geometry of the cosmos, a dimension that is as malleable and dynamic as space itself, forever intertwining the cosmic with the personal in the most profound ways. Yet even as we push the boundaries of the very large with relativity, the universe reveals its deepest secrets in the realm of the very small. To truly grasp the fabric of space-time, we must now venture into a domain so counterintuitive that it baffled even Einstein himself, the quantum world. Here we find a connection between particles that defies all conventional understanding of distance and separation, a phenomenon so strange the great physicist dismissively called it spooky action at a distance. This is quantum entanglement, and it represents one of the most validated and startling discoveries in all of modern physics. At its heart, entanglement is a profound connection. Imagine two electrons created together, their properties forever linked in a delicate quantum dance. We can then separate them, sending one on a journey to the far side of the galaxy, while we keep the other safely in a lab on Earth. According to the rules of quantum mechanics, these particles do not have definite properties like spin until the moment they are measured. The act of measurement forces the particle to choose a state. Now, here is the spooky part. The instant you measure the spin of the electron here on Earth and find it to be, say, up, its entangled partner, billions of light years away, will immediately and definitively assume the opposite spin, down. This correlation happens instantaneously, seemingly faster than the speed of light, which should be the universe's ultimate speed limit. This was the crux of Einstein's objection. He believed this implied that information was traveling between them faster than light, violating his theory of relativity. He, along with colleagues Boris Podolsky and Nathan Rosen, proposed this as evidence that quantum mechanics was an incomplete theory, that there must be some hidden variables, properties we couldn't yet see, that predetermine the particle's states all along, preserving a local reality where influences cannot travel faster than light. For decades, this remained a philosophical debate, a clash of titans about the fundamental nature of reality. That changed with the brilliant work of physicist John Stuart Bell. In the 1960s, Bell devised a cunning mathematical test, now known as Bell's theorem, that could settle the argument experimentally. Bell showed that if hidden variables existed and reality was local, then the results of certain measurements on entangled particles would have to obey a specific statistical limit, known as a Bell inequality. However, if quantum mechanics was correct and reality was truly non-local, then the measurements would violate this inequality. The experiments began, and they have only grown more precise and definitive over the years. Scientists like Elaine Aspect conducted groundbreaking tests in the 1980s, and research has continued ever since, using photons, electrons, and even small diamonds separated by ever-increasing distances. The results have been unequivocal. Time and time again, Bell's inequalities are violated. The universe has chosen a side. There are no hidden variables. The connection between entangled particles is real, instantaneous, and non-local. This doesn't mean we can send a message faster than light. The outcome of each measurement is still completely random from our perspective. We cannot force the particle on Earth to be up to send a signal. All we know is that whatever random result we get here will be perfectly correlated with the result over there. Causality is preserved. You cannot use this to create a paradox or send information into your own past. But our classical intuition about objects having independent existence is completely shattered. It suggests that at the most fundamental level, the universe is not composed of separate, isolated things, but is instead a deeply interconnected web where distance, as we understand it, might be an emergent illusion. This bizarre property is not just a theoretical curiosity. It is the beating heart of a technological revolution that is unfolding right now. The field of quantum computing relies on entanglement to perform calculations that would be impossible for any classical supercomputer. While a traditional computer bit can be either a 0 or a 1, a quantum bit or qubit can be in a superposition of both states simultaneously. But the real power emerges when you entangle multiple qubits together. Their states become linked, allowing a quantum computer to explore a vast number of possibilities in parallel, solving complex problems in cryptography, materials science, and drug discovery at an exponentially faster rate. Similarly, quantum cryptography uses the principles of entanglement to create theoretically unhackable communication systems. In a quantum key distribution system, like the one used in China's Misha satellite, entangled photons are used to generate a secret key between two parties. The beauty of this system is that any attempt by an eavesdropper to intercept the key would inevitably disturb the delicate entangled state, immediately alerting the legitimate users to the presence of an intruder. This is security guaranteed by the fundamental laws of physics itself. Perhaps the most profound implication of entanglement is its potential role in solving the greatest problem in physics, unifying gravity with quantum mechanics. This connection was stunningly proposed in a theory known as ER equals EPR, put forward by physicists Juan Maldeisner and Leonard Susskind. The ER refers to Einstein-Rosen bridges, which are the formal name for wormholes, those tunnels in spacetime we discussed earlier. The EPR refers to Einstein, Podolsky, and Rosen, the architects of the original entanglement paradox. The theory suggests that these two seemingly unrelated concepts, wormholes and entanglement, are in fact two sides of the same coin. It proposes that two particles that are entangled might not be communicating faster than light through some spooky action. Instead, they could be instantly connected because they are literally linked by a microscopic wormhole, a tiny bridge in the fabric of spacetime itself. In this breathtaking vision, the phenomenon of quantum entanglement is not some ethereal, invisible connection, but is physically encoded in the geometry of the universe. It implies that the fabric of spacetime itself might be woven together from a vast, cosmic web of quantum entanglement. This idea provides a potential pathway to finally reconcile the world of the very large, governed by gravity and general relativity, with the world of the very small, ruled by the probabilistic laws of quantum mechanics. The mysterious, non-local links between particles could be the very threads that stitch together the continuum of space and time, suggesting that the universe is far more deeply interconnected and wondrously strange than we ever could have imagined. To understand why cosmic inflation was such a revolutionary idea, we first need to grapple with the problems it was designed to solve. For decades after the Big Bang theory was established, cosmologists were puzzled by several deep mysteries about our universe. The most perplexing was the horizon problem. When we look out at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we see that it is almost perfectly uniform in temperature. The entire sky, in every direction, glows at a remarkably consistent 2.725 degrees above absolute zero. This might not seem strange until you consider the physics of information and causality. The universe simply hasn't existed long enough for light or heat to have traveled from one distant region to another to equalize their temperatures. It's as if you walked into a vast room with 1,000 people and found they all had the exact same body temperature to the thousandth of a degree, even though they had never been in contact with each other. According to the standard Big Bang model without inflation, these regions should never have been in causal contact, so how did they manage to agree on a single temperature? This was a glaring inconsistency that demanded an explanation. The second major puzzle was the flatness problem. The density of matter and energy in the universe appears to be incredibly fine-tuned to a very specific critical value. If the density were just slightly higher, the universe would have collapsed back on itself in a big crunch billions of years ago. If it were just slightly lower, matter would have flown apart so rapidly that galaxies and stars could never have formed. Instead, our universe seems to be almost perfectly flat, balanced on a razor's edge. In the old model, this would require an unimaginable degree of fine-tuning in the initial conditions of the Big Bang, a coincidence so staggering it seemed almost mystical. Physicists are deeply uncomfortable with such coincidences. They usually point to a gap in our understanding. In the late 1970s, a young physicist named Alan Guth was working on a different problem related to grand unified theories and magnetic monopoles. But in one legendary moment in 1979, he realized that a peculiar type of energy field could provide an elegant solution to all these cosmological puzzles at once. He famously wrote in his notebook that it looked like a spectacular realization and that the universe could have undergone a period of inflation. The core idea is breathtaking in its simplicity and power. Guth proposed that a fraction of a second after the initial singularity, a bizarre quantum field, often called the inflaton field, came to dominate the energy of the universe. This field possessed a peculiar property. It generated a repulsive gravitational effect, causing spacetime to expand not just quickly but exponentially. In an almost incomprehensibly short burst, lasting perhaps from 10 to the power of -36 seconds to 10 to the power of -32 seconds, the universe doubled in size at least 60 times over. To put that in perspective, if you started with a region smaller than a proton, inflation would have blown it up to something roughly the size of a grapefruit in that tiny sliver of time. This incredible growth spurt provides the elegant answers we were looking for. The horizon problem is solved because the entire observable universe was before inflation, a tiny, microscopic patch that was easily in thermal equilibrium. Inflation then took that tiny, uniform, well-mixed region and stretched it to encompass everything we can see today. The flatness problem is resolved because inflation acts like someone taking a tiny section of a giant balloon and blowing it up. Even if that original piece was a little wrinkled or curved, inflating it to an enormous size would make it appear incredibly flat and smooth, just as the surface of the Earth feels flat to us even though it's a sphere. Furthermore, this process didn't just smooth everything out. It also planted the seeds for all future structure. The quantum fluctuations that are inherent to any field were present in the inflaton field. As the universe inflated at a fantastic rate, these tiny, microscopic quantum jitters were stretched to astronomical sizes. These minute variations in density became the gravitational seeds around which all the future galaxies, stars, and planets would eventually coalesce over billions of years. The universe went from a state of smooth uniformity to one with just the right amount of lumpiness to allow for the beautiful cosmic structures we observe. The evidence for this extraordinary event is written across the sky in the cosmic microwave background. Satellites like NASA WMAP and the European Space Agency's Planck have mapped this ancient light with exquisite precision. They found exactly what inflation predicts. The universe is extraordinarily flat, and the temperature variations in the CMB are there, but they are incredibly faint, just about 1 part in 100,000. These tiny anisotropies form a very specific pattern that matches the predictions of inflationary models incredibly well. It's the fingerprint of those quantum fluctuations, magnified by inflation and imprinted onto the fabric of the cosmos. This is considered some of the strongest evidence we have for the theory. However, the search for the ultimate proof, the smoking gun, continues. Most inflationary models predict that the violent expansion would have generated a background of primordial gravitational waves, ripples in spacetime itself. These waves would have left a distinct twisting pattern known as B-mode polarization in the light of the cosmic microwave background. The hunt for this signal has been intense. In 2014, the team behind the BICEP 2 experiment, a powerful telescope at the South Pole, announced a huge discovery. They had detected this telltale pattern. For a brief, exciting moment, it seemed like the final piece of the puzzle had fallen into place. However, further analysis in collaboration with the Planck satellite team revealed that the signal they detected was almost entirely due to interstellar dust within our own Milky Way galaxy. It was a sobering lesson in the challenges of cutting-edge cosmology, where the signal you're desperately seeking can be perfectly mimicked by something as mundane as cosmic dust. The search continues with more sensitive experiments, as finding these primordial waves would not only confirm inflation but also give us a direct window into the energy scales at which it occurred, telling us about physics at energies 1,000,000,000,000 times higher than what we can achieve at the Large Hadron Collider. While cosmic inflation is the leading paradigm, it is not without its critics and alternatives. Some physicists, like Sir Roger Penrose, propose a cyclic model called conformal cyclic cosmology, where the universe goes through an endless series of eons, with the end of one becoming the Big Bang of the next. Others question the very foundations of inflation, arguing that it makes too many predictions and can be adjusted to fit almost any observation, making it difficult to falsify. Furthermore, the theory naturally leads to a profound and controversial implication, the multiverse. If inflation started, and that inflationary field had the right properties, it may never have completely stopped. The idea of eternal inflation suggests that our entire universe might be just one bubble in a vast, ever-expanding cosmic foam. Inflation could still be happening in other regions, constantly spawning new bubble universes, each with its own potentially different laws of physics. This is a staggering concept that moves from testable science to highly speculative metaphysics for some, but it is a direct consequence of the mathematics that many find compelling. Despite these debates, cosmic inflation remains the most powerful and successful framework we have for understanding the earliest moments of our universe, transforming a mysterious singularity into a dynamic, quantum-driven event that set the stage for everything that was to follow. Yet for all its profound influence, this cosmic scaffolding remains utterly invisible, a ghostly presence that we can only infer from the gravitational pull it exerts on the things we can see. The story of its discovery begins not in the depths of space, but in the careful observations of a brilliant and often overlooked astronomer, Fritz Zwicky. In the 1930s, while studying the Coma Cluster, a massive collection of over 1,000 galaxies, Zwicky noticed something bizarre. The individual galaxies within the cluster were moving so rapidly that the combined gravitational pull of all the visible stars and gas should not have been nearly strong enough to hold the cluster together. According to the laws of gravity, the cluster should have flown apart long ago. Zwicky concluded that there must be some unseen form of matter providing the extra gravity, a substance he called dunkel materie, or dark matter. His contemporaries largely dismissed the idea, but Zwicky was proven right decades later when Vera Rubin and Kent Ford made a similar, even more precise observation, but this time within individual galaxies. They meticulously mapped the rotation speeds of stars in spiral galaxies like Andromeda, expecting that stars farther from the galactic center, where visible matter is more sparse, would orbit more slowly, just as Pluto orbits the Sun more slowly than Earth. To their astonishment, they found that the orbital speeds of these outer stars remained high and flat. They did not drop off. This could only mean one thing. Each galaxy is embedded within a massive, invisible sphere of matter, a dark matter halo, that extends far beyond the visible edge of the galaxy, its gravity keeping the outer stars whipping around at unexpectedly high speeds. This revelation transformed our understanding of galaxies from mere collections of stars to islands of light, adrift in a vast, unseen sea of mysterious material. So what could this invisible substance actually be? The leading hypothesis points to entirely new kinds of particles that lie beyond the standard model of particle physics. These particles would have to be dark, meaning they do not interact with light or electromagnetic forces at all, and they would need to be cold, moving relatively slowly in the early universe to allow gravity to clump them together and form the seeds of galaxies. Prime candidates are WIMP, or weakly interacting massive particles. These are theoretical heavy particles that would interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. For decades, physicists have built exquisitely sensitive experiments deep underground to shield them from cosmic rays, hoping to catch the extremely rare bump of a WIMP colliding with an atomic nucleus in a vat of ultra-pure liquid xenon. Experiments like LUX Xenon and Panda X have pushed the boundaries of sensitivity, but so far they have not found a definitive signal. Another promising candidate is the Action, a hypothetical extremely light particle originally proposed to solve a different problem in quantum physics. Actions would behave less like discrete particles and more like a pervasive, wave-like field throughout space. If they exist, they could be detected by observing their very subtle conversion into photons in the presence of a powerful magnetic field. While these direct detection experiments have yet to find proof, their relentless pursuit continues to narrow the possibilities, inching us closer to perhaps the greatest discovery in modern physics. Perhaps the most stunning and direct evidence for the existence of dark matter came not from a lab or a single galaxy, but from a colossal cosmic collision. In 2006, astronomers observed a system known as the Bullet Cluster, which is actually two galaxy clusters that have violently slammed into each other. This event provided a near-perfect natural experiment. Using the Chandra X-ray Observatory, scientists could see the hot, luminous gas from each cluster, the normal baryonic matter which collided and slowed down during the impact, much like two clouds of smoke would in a car crash. But by using the technique of gravitational lensing, which maps the total mass distribution by observing how the cluster's gravity bends light from background galaxies, they could see where the majority of the mass actually ended up. The result was breathtaking. The lensing maps revealed that the bulk of the mass had sailed right through the collision unscathed, completely separated from the luminous gas. This was a direct visual demonstration that most of the matter in the clusters is collisionless and dark. It does not interact with itself or with normal matter in any way other than through gravity. The Bullet Cluster observation effectively ruled out alternative theories that attempted to explain the missing gravity by modifying the laws of gravity itself, such as modified Newtonian dynamics or MN. It showed conclusively that the anomaly is not with our understanding of gravity, but with the composition of the universe itself. A significant portion of its matter is simply made of something else, something entirely foreign to our experience. The role of dark matter is not just that of a silent partner, it is the master architect of the entire cosmic web. In the early universe after the inflationary period, the distribution of matter was almost perfectly smooth, but not quite. Tiny quantum fluctuations stretched to cosmic size by inflation created minute ripples in the density of the cosmos. Dark matter, being cold and unaffected by the intense radiation pressure that buffeted normal matter, was the first to respond to gravity. It began to collapse into these slightly denser regions, forming vast gravitational wells. It was only later that normal matter, in the form of hydrogen and helium gas, could fall into these pre-existing dark matter potential wells. Once there, the gas could cool, condense, and eventually ignite into the first stars and galaxies. Without the gravitational scaffolding provided by dark matter, the universe would have remained a diffuse, featureless soup. There simply wouldn't have been enough time for the attractive force of gravity, acting on visible matter alone, to pull together structures as massive as galaxies within the age of the universe. This intricate relationship is revealed through modern computer simulations of cosmic evolution. When scientists run models that include only normal matter, the resulting virtual universe looks nothing like our own. But when they add the correct amount of cold dark matter, the simulations miraculously produce a familiar cosmic web of filaments, voids, and clusters that beautifully matches the large-scale structure we observe in galaxy surveys. This invisible framework is the true backbone of the cosmos, the hidden structure upon which the visible universe is built, and unlocking its identity is the key to understanding the very architecture of reality. Now let's journey from the cosmic scaffolding of dark matter to a concept that challenges our most basic perception of reality itself. What if everything we see and experience in our rich, three-dimensional world, the depth of a forest, the vastness of a galaxy, the solidity of your own hand, was nothing more than a projection, a kind of cosmic illusion? This isn't a plot from a science fiction movie. It's a serious scientific idea known as the holographic principle, and its origins are as strange as they are profound. The story begins not with holograms, but with one of the most perplexing puzzles in physics: what happens to information when it falls into a black hole? In the 1970s, a young physicist named Jacob Bekenstein made a startling proposal. He argued that a black hole must have entropy. Entropy is a measure of disorder or information content, and Bekenstein realized that a black hole's entropy wasn't proportional to its volume, as one might expect, but to the surface area of its event horizon. This was a bizarre suggestion. It implied that all the information needed to describe everything that had ever fallen into a black hole wasn't lost inside its infinite depth, but was somehow encoded on its two-dimensional boundary, like a message etched onto a spherical shell. Stephen Hawking initially disagreed, but his own discovery of Hawking radiation, which showed black holes could evaporate, brought the problem into sharp focus. If a black hole evaporates and disappears, what happens to all that information? The holographic principle, championed by physicists Gerard T. Hooft and Leonard Susskind, emerged as a radical solution. It boldly asserts that the information within any region of space is entirely encoded on its lower dimensional boundary. Think of a more familiar hologram like the one on your credit card. A two-dimensional plastic film creates the stunning illusion of a three-dimensional image floating in space. The holographic principle suggests our entire universe might operate on a similar, though vastly more complex, principle. The three spatial dimensions we experience could be a projection from a two-dimensional surface at the very edge of the cosmos, a surface that contains all the information needed to describe everything within it. This means the universe might fundamentally have only two dimensions, and the third is an emergent property, a grand and convincing illusion. This idea finds its most rigorous formulation in a discovery by physicist Juan Maldacena, who proposed a specific mathematical duality known as the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT for short. While the details are intensely complex, the core concept is mind-bending. Maldacena showed that a gravitational theory describing a hypothetical universe with certain properties, a kind of bulk space, is completely equivalent to a quantum field theory without gravity operating on that universe's lower dimensional boundary. It's like finding a perfect dictionary that translates a book written in the language of gravity and dimensions into a completely different book written in the language of quantum particles on a flat surface. Every event, every particle, every force within the volume has a perfect corresponding description on the boundary. This provides a concrete mathematical framework for the holographic principle, suggesting that gravity itself might not be a fundamental force but an emergent phenomenon that arises from quantum interactions playing out on a distant, lower dimensional surface. While our actual universe doesn't perfectly match the specific hypothetical one in Maldacena's model, the correspondence is so powerful and compelling that many physicists believe a similar holographic description must underlie our own reality. It offers a tantalizing pathway to finally reconciling Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small, by showing they might be two different perspectives on the same underlying truth. But how could we ever test such an abstract and seemingly untestable idea? Scientists are nothing if not ingenious, and they have begun to explore laboratory-based analogues of holography. One fascinating area of research involves certain exotic materials known as strange metals and high-temperature superconductors. These materials have bizarre properties that are incredibly difficult to model using standard quantum physics. Intriguingly, when physicists apply the mathematical tools developed for the AD/S/CFT correspondence, effectively treating the material as a lower dimensional boundary of a higher dimensional gravitational system, they can accurately calculate and predict the behavior of these strange metals, such as how their electrical resistance changes with temperature. It's as if the complex collective behavior of billions of electrons in a three-dimensional chunk of material is being guided by rules written on a two-dimensional surface. These experiments don't prove our universe is a hologram, but they provide a stunning validation of the mathematical machinery behind the principle. They show that holographic duality is not just abstract math. It's a powerful practical tool that can solve real-world problems in physics, suggesting that the line between the fundamental and the emergent might be far blurrier than we ever imagined. This forces us to confront a deeply philosophical question about the nature of reality itself. Is the world we perceive, with its rich tapestry of sights, sounds, and sensations, the true, fundamental reality? Or is it a secondary phenomenon, a magnificent projection from a simpler, more fundamental layer of existence that operates in fewer dimensions? The holographic principle doesn't yet provide a definitive answer, but it radically expands the horizon of what is possible, inviting us to consider that the universe's greatest secrets might not be hidden in the stars, but in the very nature of information and how it defines the space we call home. But if black holes represent the ultimate cosmic sinkhole, a one-way street where matter and energy vanish forever, what about the opposite? What if the universe has a source as well? This brings us to one of the most speculative and fascinating ideas in theoretical physics, the white hole. In the precise, elegant mathematics of Einstein's general relativity, the equations that describe a black hole are, for the most part, time-symmetric. This means if you were to take the equation and mathematically reverse the direction of time, you would get a new, equally valid solution. This time-reversed version of a black hole is what we call a white hole. Imagine a black hole in reverse. Instead of an event horizon from which nothing can escape, a white hole would possess an event horizon from which nothing can enter. It would be a region of space-time that violently ejects matter and energy out into the universe, while utterly refusing to let anything back in. It's a cosmic gusher, an erupting geyser of reality itself, theoretically spewing out everything that a black hole might have swallowed. While a black hole is defined by its immense, inescapable pull, a white hole would be characterized by an irresistible, explosive push, a region of space that is utterly off-limits to visitors. The mathematical existence of white holes is undeniable within the framework of general relativity, but their physical plausibility is a subject of intense debate. Most physicists consider them to be highly unstable mathematical curiosities rather than real objects we might one day observe. The primary issue is one of formation. We have a very clear understanding of how a black hole forms, the gravitational collapse of a massive star or the merger of dense objects, but how would a white hole come into being? It can't form from collapse. It would have to somehow erupt into existence already fully formed, which violates our intuitive understanding of cause and effect. Furthermore, any ordinary matter that fell onto a white hole would be met with such ferocious outward pressure that it would likely cause the entire structure to collapse almost instantly into a black hole. Their sheer instability is the main reason why, despite decades of searching, we have not a single piece of observational evidence that they exist. They remain ghosts in the equations, tantalizing possibilities that the universe seems to actively avoid. However, their theoretical allure is too powerful to ignore, leading to some extraordinary speculative models. One compelling idea connects white holes to the ultimate fate of black holes. Through the process of Hawking radiation, a black hole slowly loses mass over astronomical timescales, eventually evaporating away completely. But what is the final endpoint of this evaporation? Some physicists, like Carlo Rovelli, have proposed that the immense quantum gravitational pressure at the very end of a black hole's life could cause it to undergo a dramatic quantum bounce, effectively transforming into a white hole. In this scenario, the information that fell into the black hole wouldn't be lost. After a phenomenally long time, it would be explosively released back into the universe. This would provide an elegant solution to the black hole information paradox, preserving the fundamental laws of quantum mechanics. Another fascinating speculation paints on an even grander canvas, suggesting that the Big Bang itself could be viewed as a white hole event. The initial singularity from which our entire universe erupted shares a striking mathematical resemblance to a white hole, a point of infinite density from which all energy and spacetime emerged, and a past boundary that nothing could have entered. This perspective reframes the beginning of everything not as a point in pre-existing space, but as the explosive birth of space and time from a white hole singularity. The existence of white holes would force us to confront profound questions about the nature of time and causality. Our everyday experience is that time has a definite arrow. Eggs scramble but never unscramble, and we remember the past but not the future. The laws of physics, however, are almost entirely time-symmetric at a fundamental level. White holes are a stark embodiment of this tension. If they are simply black holes running backwards in time, then their existence implies that the distinction between past and future might be far less fundamental than we think. It challenges the very notion of causality, potentially allowing for effects that precede their causes in a way that could unravel the logical consistency of the universe. This is why many scientists believe that if white holes are ever found, it will not be within classical general relativity, but within a successful theory of quantum gravity, where the bizarre rules of the quantum world might provide a stable framework for these paradoxical objects to exist. Detecting one would require looking for an entirely new class of astronomical phenomenon, perhaps a sudden, inexplicable eruption of high-energy particles or a burst of gravitational waves with no corresponding collision event, a shout in the cosmos with no visible source. For now, white holes remain a powerful thought experiment, a tool for stretching our understanding of physics to its absolute limit and asking what is truly possible in the strange and wonderful universe we inhabit. But this relentless march from past to future is perhaps the most fundamental and puzzling feature of our existence. Why can we remember yesterday but not tomorrow? Why does a shattered glass never spontaneously reassemble itself? This one-way street of reality is what physicists call the arrow of time, and its origin is one of the deepest enigmas in all of science. At first glance, the answer seems to lie in a concept from thermodynamics known as entropy, which is a measure of disorder or randomness in a system. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. A tidy room gathers dust, a hot cup of coffee cools to room temperature, and a star eventually burns out. These are all examples of the universe moving from a state of lower entropy to higher entropy, from order to disorder. This gives us a powerful and intuitive explanation for why time seems to have a direction. It's the direction in which disorder increases. We can easily see the past in the ordered state and the future in the disordered one. Here's where the mystery deepens. If we look at the fundamental laws of physics that govern the interactions of individual particles, whether it's Newton's laws of motion, Einstein's equations of relativity, or the Schrödinger equation of quantum mechanics, they are almost entirely time-symmetric. They work perfectly well whether time is running forward or backward. If you were to watch a film of two billiard balls colliding and ricocheting off each other, and then someone played the film in reverse, the motion would still look completely natural and obey all the laws of physics. The microscopic laws don't care about the arrow of time. So why does the macroscopic world we live in have such a strong preference for one direction? The key lies not in the laws themselves, but in the initial conditions of our universe. For the arrow of time to emerge from time-symmetric laws, the universe must have started in an incredibly unique, highly ordered, and therefore very low entropy state. Think of it like a new deck of cards perfectly sorted by suit and number. If you shuffle it, it becomes disordered, and it's extremely unlikely to ever return to that perfectly ordered state through more shuffling. The Big Bang, it seems, dealt the cosmic deck in a state of exquisite order. This presents a monumental puzzle for cosmologists. Why was the early universe in such a special, low entropy state? Physicist Sean Carroll, among others, explores how the theory of cosmic inflation might provide an answer. Inflation, that period of fantastically rapid expansion in the first fraction of a second after the Big Bang, would have stretched a tiny, smooth patch of spacetime into our entire observable universe. This process would have effectively reset the entropy, smoothing out any wrinkles and creating that low entropy starting point from which everything else could unfold. The expansion of the universe itself then provides the mechanism that allows entropy to continually increase, creating the arena for the arrow of time. As space stretches, it creates ever more room for disorder to grow, ensuring that the future will always be more disordered than the past. This leads to a staggering possibility. If our universe is just one bubble in a vast multiverse, the arrow of time might not be a universal constant. In other bubbles beyond our horizon, the initial conditions might have been different. Perhaps in some of those universes, time flows in the opposite direction from our perspective. Or maybe those realms are in a state of equilibrium where entropy doesn't change and the very concept of a temporal direction is meaningless. This isn't just an abstract physics problem. It cuts to the core of human experience and philosophy. Our conscious perception of time, the flow of moments, the formation of memories, the anticipation of the future is deeply intertwined with the thermodynamic arrow. We remember the past because it is a state of lower entropy, and the formation of a memory is a process that increases disorder in the brain and its surroundings. Causality, the principle that a cause must precede its effect, is also bound to this arrow. It's impossible to imagine an effect happening before its cause because that would require a decrease in entropy, which is overwhelmingly improbable. Some philosophers and physicists, like Julian Barber, have even argued that time itself is an illusion, an emergent property that arises from the changing relationships between objects rather than a fundamental river that flows. In the block universe theory of relativity, all of time, past, present, and future exists simultaneously in a static four-dimensional block. The feeling of now moving forward is just a peculiar feature of our conscious observation within that block. The arrow of time forces us to confront the strange disconnect between the world as described by our most fundamental physical theories and the world as we experience it every moment of our lives, a reminder that some of the universe's greatest secrets are hidden in plain sight. woven into the very fabric of our reality. For centuries, our understanding of planets was limited to the 8, now 9, that orbit our own sun. We could only speculate about what other stars might host, wondering if our solar system was a cosmic standard or a bizarre outlier. That all changed dramatically in the last 3 decades, launching us into a golden age of discovery that has fundamentally rewritten the textbooks on planetary science. We now know that planets are not the exception but the rule. The galaxy is teeming with them, a diverse menagerie of worlds so strange and varied they defy the imagination. This incredible revelation began in earnest in 1992 with the first confirmed detection of planets orbiting a pulsar, a dead star, and then exploded in 1995 with the discovery of 51 Pegasi b, a hot Jupiter orbiting perilously close to its sun. This proved that not only did other planets exist, but they could exist in configurations utterly unlike anything in our own cosmic neighborhood. The true game-changer, however, was the launch of NASA's Kepler Space Telescope in 2009. Kepler's mission was simple yet profound: to stare fixedly at a single patch of sky containing over 150,000 stars, watching for the telltale, periodic dimming that occurs when a planet passes in front of its host star. This technique, known as transit photometry, allowed Kepler to conduct a cosmic census, and the results were staggering. It revealed that there are more planets than stars in our galaxy, with billions of potentially rocky worlds orbiting within the habitable zones of their stars. The universe, it seems, is overflowing with real estate. The most tantalizing of these discoveries are the planets found within what astronomers call the habitable zone, often nicknamed the Goldilocks zone. This is the region around a star where conditions are just right, not too hot and not too cold, for liquid water to potentially exist on a planet's surface. Water, as we understand it, is the essential solvent for life as we know it, making these zones the primary hunting ground in our search for alien biology. One of the most promising systems discovered is TRAPPIST-1, a cool, dim red dwarf star located about 40 light-years away. Around it whirls a family of 7 Earth-sized planets, and an astonishing 3 of them orbit squarely within the star's habitable zone. Imagine the view from the surface of one of these worlds, a sky dominated by a large, dull red sun, with the other 6 planets appearing as distinct orbs, some perhaps showing visible features like our own moon. Because the star is so cool, its habitable zone is much closer in than our sun's, meaning these planets are likely tidally locked, with one side in perpetual daylight and the other in endless night. This would create extreme weather patterns, with potentially habitable conditions existing in the twilight band between the 2 hemispheres. The existence of such a compact, Earth-sized system immediately raised the possibility that life could arise in environments very different from our own, expanding our definition of what a habitable world might look like. Finding these distant specks of rock and gas is a monumental feat of engineering and ingenuity, requiring incredibly precise methods to detect the faint signals of a planet from light-years away. The 2 most successful techniques are transit photometry and the radial velocity method. Transit photometry, as used by Kepler and now the TESS mission, is like detecting a gnat flying in front of a searchlight from miles away. As a planet transits its star, it blocks a tiny fraction of the star's light, causing a minute but measurable dip in brightness. The depth of this dip reveals the planet's size relative to its star. The radial velocity method, on the other hand, watches for the star's subtle wobble. A planet doesn't just orbit a star, they both orbit a common center of mass. The gravitational tug of an orbiting planet causes the star to move slightly toward and away from us. This motion induces a Doppler shift in the star's light, stretching it slightly redder as it moves away and bluer as it moves closer. By carefully measuring this shift, astronomers can determine the planet's mass and orbital period. Each method provides a different piece of the puzzle. Transits give us size, and radial velocity gives us mass. Together, they allow us to calculate the planet's density, telling us if it's a gaseous world like Jupiter, an icy giant like Neptune, or a rocky planet like Earth. The next great leap in this field is already underway, moving from simply detecting planets to truly characterizing them. This is the realm of atmospheric spectroscopy, and it's the primary mission of telescopes like the James Webb Space Telescope. When a planet transits its star, a tiny fraction of the star's light filters through the planet's atmosphere if it has one. Different molecules in the atmosphere absorb light at very specific wavelengths. By splitting that filtered light into a spectrum, a rainbow of wavelengths, scientists can search for the unique chemical fingerprints of gases like water vapor, methane, carbon dioxide, and oxygen. The presence of certain combinations of these gases could be a powerful, albeit indirect, sign of life. For instance, finding an atmosphere rich in both oxygen and methane would be highly suspicious, as these gases react with each other and would quickly cancel out unless they were being continuously replenished, potentially by biological processes. Such a combination would be a potential biosignature, a sign that something on that world is actively altering its atmosphere in a way that is difficult to explain through geology alone. The search for these biosignatures is the holy grail of exoplanet science, a direct hunt for evidence that we are not alone in the universe. The sheer diversity of worlds we've found has shattered any notion that our solar system is a typical model. We've discovered planets that defy classification, like hot Jupiters, gas giants orbiting closer to their stars than Mercury does to our Sun, with atmospheres hot enough to vaporize iron. We've found super-Earths, rocky planets larger than our own but smaller than Neptune, a class of world that doesn't even exist in our solar system. Some planets orbit two stars at once, like the fictional Tatooine from Star Wars, while others are rogue planets untethered to any star, drifting through the eternal cold of interstellar space. This incredible variety tells us that the process of planet formation is both robust and incredibly creative, capable of producing an endless array of outcomes depending on the initial conditions of the stellar nursery. It suggests that solar systems like our own, with an orderly arrangement of small, rocky planets inward and gas giants outward, might be just one possible configuration among many, not necessarily the most common. This avalanche of discovery brings the Fermi paradox into sharper focus than ever before. With hundreds of billions of stars in our galaxy, and now knowing that most have planets, many of which are Earth-sized and in the habitable zone, the statistical argument for life elsewhere seems overwhelming. The universe appears to have provided plenty of time and plenty of suitable real estate for life to arise repeatedly. So, the question posed by physicist Enrico Fermi echoes more loudly across the decades: where is everybody? The silence from the cosmos is perplexing. The continued absence of any definitive evidence for intelligent life, despite our increasingly sophisticated searches, suggests that there might be a great filter, a barrier that is extremely difficult for life to overcome. This filter could be behind us, meaning the emergence of intelligent life is astronomically rare. Or, more ominously, it could be ahead of us, a common catastrophe like self-destruction through technology that every advanced civilization eventually encounters. The ongoing discovery of exoplanets doesn't solve the paradox. It deepens it, turning it from a philosophical musing into a pressing scientific question that we are now equipped to investigate. Perhaps no single discovery has made the search for life feel more immediate than that of Proxima Centauri b. Located a mere 4.2 light-years away, it orbits within the habitable zone of Proxima Centauri, the closest star to our Sun. This isn't a distant, abstract world. It is, in galactic terms, right next door, while it orbits a volatile red dwarf star that likely bathes it in harmful flares, and it may be tidally locked. Its mere existence so close by has ignited serious discussions about interstellar exploration. Projects like Breakthrough Starshot, which aims to send tiny, laser-propelled probes on a flyby mission to the Alpha Centauri system within a generation, are no longer pure science fiction. They are ambitious, long-shot engineering proposals driven by the tantalizing possibility of having an actual target to study up close. Proxima Centauri b represents the embodiment of a new era, a tangible destination that forces us to look beyond our solar system and dream of the day when we might finally get a close-up glimpse of another world that could harbor the ingredients for life, fundamentally changing our perspective on our place in the cosmic ocean. To grasp the sheer density of a neutron star, try to picture squeezing the entire mass of our Sun, a sphere over 860,000 miles across, down into a ball no larger than a city like Manhattan. The result is an object so unimaginably compact that a single sugar cube-sized fragment of it would weigh billions of tons here on Earth, a mass comparable to that of every single human being on the planet combined. This incredible density is the aftermath of a supernova, the cataclysmic death of a massive star. When such a star exhausts its nuclear fuel, the outward pressure from fusion can no longer hold back the immense crush of gravity. The core collapses in less than a second, and the force is so extreme that it smashes electrons and protons together, fusing them into neutrons and neutrinos. What remains is a vast, seething ocean of these subatomic particles, a material state so exotic it's often called neutronium, where matter is pressed up against the absolute limits of physical law, governed by quantum degeneracy pressure rather than the familiar chemistry of atoms. This extreme environment gives rise to two of the most powerful forces in the universe, gravity and magnetism. The surface gravity on a neutron star is about 100 billion times stronger than Earth's, enough to warp light itself into a visible lensing effect and to crush any known material into a featureless, perfectly smooth surface. Even more astonishing are the magnetic fields. Some neutron stars, known as magnetars, possess magnetic fields that are 1,000 trillion times more powerful than Earth's. These fields are so intense they could wipe the data from every credit card on the planet from halfway across the Milky Way, and their slow decay releases titanic bursts of X-rays and gamma rays, making magnetars some of the most violently energetic objects we have ever observed. When a neutron star is born spinning from the asymmetric collapse of its progenitor star, this combination of rapid rotation and intense magnetic field creates one of astronomy's most useful tools, the pulsar. Imagine a cosmic lighthouse where the beam isn't made of light but of intense radio waves, X-rays, or even gamma radiation. As the neutron star spins, this beam sweeps across the sky, and if Earth happens to lie in its path, we detect a perfectly regular pulse of energy with every rotation. Some pulsars spin hundreds of times per second, their timing so precise they rival atomic clocks. This incredible regularity allows astronomers to use them as navigational beacons to probe the interstellar medium, test the theories of general relativity by observing how their signals are affected by orbiting companions, and even to search for the faint ripples in spacetime known as gravitational waves by looking for minuscule timing discrepancies in networks of these cosmic metronomes. The true power of neutron star research was revolutionized on August 17, 2017, when gravitational wave observatories LIGO and Virgo detected the ripples from two neutron stars colliding, an event designated GW 170817. For the first time, astronomers could point traditional telescopes at the location of a gravitational wave source and witness the cosmic aftermath across the entire electromagnetic spectrum. What they saw was a kilonova, a brilliant explosion far brighter than a nova but less than a supernova. The intense conditions of the merger forged a cauldron of heavy elements through a process known as rapid neutron capture, or the R process. In mere seconds, this single event produced and scattered into space an amount of gold and platinum many times the mass of our entire planet, along with other precious elements like uranium. This one observation provided the long-sought answer to a fundamental question: the origin of the heaviest elements in the periodic table. The gold in your jewelry and the platinum in a catalytic converter were almost certainly forged in the violent merger of two neutron stars billions of years in the past. Beyond creating the elements of our world, these mergers are also the suspected engines behind short-duration gamma-ray bursts, some of the most energetic explosions in the cosmos since the Big Bang itself. The collision of neutron stars is thought to create a rapidly spinning black hole surrounded by a torus of leftover neutron-rich material, and as this material falls in, it launches jets of particles moving at nearly the speed of light. If one of these jets is pointed directly at Earth, we observe a blinding flash of gamma rays that, for a few seconds, can outshine every star in the universe combined. GW 170817 confirmed this connection, as a gamma-ray burst was detected from the same location just 1.7 seconds after the gravitational wave signal arrived. Perhaps most profoundly, neutron stars serve as unparalleled natural laboratories for testing nuclear physics under conditions that could never be replicated on Earth. The interior of a neutron star remains one of physics' greatest mysteries. Is it a superfluid sea of neutrons, or does the pressure become so immense that neutrons themselves break down into a soup of even more fundamental quarks, creating a quark star? The answer lies in the equation of state of ultra-dense matter, which describes how matter behaves under such extreme pressure. By carefully measuring the masses and radii of neutron stars, often by observing how their intense gravity bends the light from companions or how they emit X-rays, scientists can rule out various theoretical models. The data from events like GW 170817 place crucial constraints on the size and deformability of these objects, telling us just how squishy or rigid neutron star material truly is. Each observation brings us closer to understanding the very nature of matter itself, probing a frontier where the familiar rules of physics dissolve into the unknown. Now let's journey from the crushing densities of neutron stars to the grandest possible structures in the cosmos, flaws in the very fabric of reality itself, left over from its fiery birth. To understand cosmic strings, we need to rewind the clock to the universe's very first moments, a time of almost inconceivable energy and change. In its earliest instance, the universe was a searingly hot, unified plasma where all the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, were merged into a single superforce. As the cosmos expanded and cooled, it underwent a series of profound phase transitions, much like steam condensing into water or water freezing into ice. But here, it was the fabric of space-time itself that was changing state. During these transitions, the underlying fields that govern the universe had to settle into a new, stable configuration. And just as ice forming on a pond can develop cracks and fissures, these cosmic phase transitions were not always perfectly smooth. In some theoretical models, particularly grand unified theories that attempt to merge the electromagnetic and nuclear forces, these transitions could have created persistent, stable defects, one-dimensional cracks frozen into the structure of spacetime. These are cosmic strings not made of any material substance, but of pure, concentrated energy, thinner than a proton but stretching across the entire observable universe. The properties of these objects are as mind-bending as their origin. A cosmic string would be a true singularity, a one-dimensional line of immense mass energy. You could theoretically loop one around a planet, and its gravitational pull would be so intense that if you moved a spaceship around this loop, you could return to your starting point before you even left, effectively creating a time machine. The string's density is so colossal that just a single kilometer of it might weigh as much as an entire planet. Despite this immense mass, a straight cosmic string would exert no net gravitational pull on surrounding objects. Its gravity would be purely lateral, meaning objects would be drawn toward it from the sides but not accelerated along its length. However, if a string were to oscillate or form a loop, it could radiate a tremendous amount of energy in the form of gravitational waves, potentially providing a powerful, continuous source for observatories like LIGO to detect. These loops would gradually lose energy and shrink through this radiation, eventually vanishing in a burst of waves, a process that could still be ongoing today from strings formed in the early universe. If these exotic relics do exist, how could we ever hope to find them? Their most distinctive calling card would be a dramatic effect on light known as gravitational lensing. The immense density of a cosmic string would warp the spacetime around it so severely that it would act like a perfect, linear lens. Imagine looking at a distant galaxy and seeing not one, but two identical images of it, perfectly mirrored along a perfectly straight line. This double image effect would be a smoking gun, unlike the more common and smeared lensing caused by spherical objects like black holes or dark matter halos. Furthermore, a cosmic string drifting through space would create a unique and sudden discontinuity in the cosmic microwave background, the ancient afterglow of the Big Bang. As the string's gravitational well passes through, it would create a very sharp, linear step or tear in the temperature of the CMB, a signature that satellites like Planck have actively searched for. While a few tentative anomalies have been spotted over the years, none have been confirmed, and the hunt continues with ever more sensitive instruments. The potential discovery of even a single cosmic string would be a monumental breakthrough, providing direct, tangible evidence for physics at energy scales a trillion times beyond what we can probe in particle colliders. Beyond their value as a fossil from the universe's first second, cosmic strings could have played an active and crucial role in shaping the cosmos we see today. In the early universe, matter was spread almost perfectly smoothly. For galaxies and clusters to form, there needed to be tiny seeds of density, slight gravitational wells to attract and gather the primordial gas. While quantum fluctuations from inflation are the leading theory for these seeds, cosmic strings could have provided an alternative mechanism. As these massive strings moved through the early universe, their immense gravity would have dragged normal matter along behind them, creating dense wakes that could have collapsed into the first protogalaxies. In this scenario, the entire large-scale structure of the universe, the vast cosmic web of filaments and voids, could be a direct trace of a network of strings that has since decayed away. Finding evidence for strings could therefore force us to rewrite our understanding of how everything, including our own Milky Way, came to be, offering a completely different narrative for the origin of cosmic structure that connects the very largest scales directly to the physics of the very first moment. Yet after all this discovery, after finding that the cosmos is overflowing with real estate, we are met with a profound and unsettling silence. We have built giant radio telescopes and trained them on the stars, listening for any whisper of artificial signal, any sign that we are not alone in this vast, dark ocean. And so far, we have heard nothing but the natural background hum of the universe. This glaring contradiction between the high probability of extraterrestrial life and the complete absence of any evidence for it is one of the most enduring puzzles in science, known famously as the Fermi paradox. It gets its name from a casual lunchtime remark by physicist Enrico Fermi in the 1950s. After contemplating the sheer number of stars and the potential for ancient civilizations, he simply asked, "Where is everybody?" His point was piercingly simple. If intelligent life is common, the galaxy should have been colonized many times over by now. The fact that we see no signs of this forces us to confront some deeply unsettling possibilities about the nature of life and intelligence in the cosmos. To even begin grappling with this paradox, scientists often turn to a powerful, though highly speculative, tool known as the Drake equation. Formulated by astronomer Frank Drake, it's not so much a solvable formula as it is a structured way to think about all the factors involved in the emergence of a detectable civilization. The equation multiplies a series of variables: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life actually appears, the fraction where life becomes intelligent, the fraction that develops technology that releases detectable signs, and finally, the length of time such civilizations release those signs into space. The problem is that most of these factors remain complete unknowns. We are now filling in the early terms with data from telescopes like Kepler, learning that planets are plentiful and that habitable zones are common. But the later terms, those concerning the origin of life, the rise of intelligence, and the longevity of civilizations, are still a vast mystery. We have a sample size of one ourselves. The Drake equation beautifully frames the problem, but it doesn't solve it. It simply shows us all the doors we have yet to open. This silence has spawned a spectrum of potential solutions, ranging from the hopeful to the terrifying. One of the most optimistic is the idea that space is simply big, unimaginably, mind-numbingly big. The distances between stars are so vast that even if the galaxy is teeming with life, the sheer energy and time required for travel or communication might make it impractical. Civilizations might be like islands in an endless ocean, aware of each other's potential existence but separated by an uncrossable sea of space and time. Another, more introspective idea is the zoo hypothesis. This suggests that advanced civilizations are indeed aware of us, but they have chosen to place our planet in a kind of cosmic quarantine, observing us from a distance without interference to allow our species to develop naturally. It's a peaceful, almost paternalistic explanation, implying a universal ethical code among older species to avoid contaminating or disrupting emerging cultures like our own. Then there are the darker answers, the ones that serve as a stark warning for our own future. The most chilling of these is the concept of the Great Filter. This theory proposes that there is some kind of barrier, an evolutionary or technological challenge that is extremely difficult to overcome, which prevents life from progressing to the point of interstellar colonization. The frightening question is whether that filter is behind us or ahead of us. Is the Great Filter something like the origin of life itself? Perhaps the jump from non-living chemistry to a self-replicating cell is so astronomically unlikely that it almost never happens, making us a miraculous fluke. Or is the filter the emergence of multicellular intelligence? Or, most ominously, is the filter still ahead of us? This is the possibility that almost all advanced civilizations inevitably destroy themselves upon discovering a certain level of technology. whether through nuclear war, environmental catastrophe, uncontrollable artificial intelligence, or some other technological nightmare we haven't even conceived of yet. In this scenario, the silence of the universe is a graveyard, and the question, "Where is everybody?" has a tragically simple answer. This profound mystery is what fuels the ongoing work of organizations like the Search for Extraterrestrial Intelligence, or SETI. For decades, these projects have scanned the skies, sifting through the radio noise of the universe for any pattern, any signal that bears the unmistakable signature of intelligence. While there have been a few tantalizing false alarms like the famous "wow" signal, nothing has ever been repeated or confirmed. Today, the search is broader and more sophisticated than ever, encompassing not just radio waves but also optical lasers, and even looking for potential megastructures, like hypothetical Dyson spheres that might be built by civilizations harnessing the entire energy of their star. The silence so far isn't discouraging. It simply tells us we need to look harder, smarter, and in more ways. It's a puzzle that pushes the very limits of our technology and our imagination. Ultimately, the Fermi paradox is more than just an astronomical question. It's a mirror held up to humanity. It forces us to reflect on our own trajectory, our own technological adolescence, and our own potential future. Are we on the cusp of breaking through to become a vocal galactic species, or are we unknowingly approaching our own great filter? The silence invites us to consider the fragility of intelligence and the profound responsibility that comes with technological power. It challenges us to grow wiser, to navigate the dangers of our own invention, and perhaps one day to become the ones who break the silence, finally answering Fermi's question with a signal that says, "We are here." Yet for all their individual triumphs, these two pillars of physics are built on fundamentally different foundations, and when pushed to their absolute limits, they clash in a conflict that threatens our very understanding of reality. This great divide becomes most apparent in the most extreme environments the universe has to offer. At the heart of a black hole, general relativity predicts a point of infinite density, a singularity where the laws of physics break down completely. And in the first fleeting moments of the Big Bang, the entire cosmos was compressed into such a scorching, dense state that neither theory can fully describe what occurred. In these realms, the smooth, geometric fabric of spacetime described by Einstein becomes a chaotic, frothing sea of quantum fluctuations. To truly understand these events, we need a theory that can marry the large-scale elegance of gravity with the small-scale weirdness of the quantum world. This monumental challenge, the quest for a theory of quantum gravity, is perhaps the single greatest unsolved problem in all of physics, a puzzle that has consumed the brightest minds for nearly a century. One of the most ambitious and well-known approaches is string theory. This framework proposes a radical shift in how we view the fundamental building blocks of the universe. Instead of point-like particles, string theory suggests that at the very smallest scales, everything is composed of tiny, vibrating loops of energy strings. Much like a single violin string can vibrate at different frequencies to produce distinct musical notes, these fundamental strings vibrate in different modes to manifest as all the different particles we observe. The electron would be one note, the quark another, and the photon yet another. This elegant idea naturally incorporates gravity, with the graviton, the hypothetical particle carrying the gravitational force, emerging as another specific vibration. However, this beauty comes with a staggering requirement. For the mathematics of string theory to work consistently, the universe must have more than the 3 spatial dimensions we experience. Most versions require 10 or even 26 dimensions, with the extra dimensions curled up into shapes so tiny they are undetectable. While string theory offers a compelling vision of unification, it has been criticized for a lack of testable predictions and for the existence of a vast number of possible solutions, often called the string landscape, which some argue makes it less a definitive theory and more a fascinating mathematical framework. In stark contrast to string theory's extra dimensions, another promising candidate takes a more minimalist approach. Loop quantum gravity does not try to reinvent the particles of the standard model, but instead focuses on quantizing the very stage upon which they play, spacetime itself. Imagine the smooth, continuous fabric of spacetime not as a fundamental reality, but as an emergent property, much like the smooth surface of a lake emerges from the frantic motion of countless water molecules. Loop quantum gravity proposes that space is not infinitely divisible, but is instead composed of tiny, discrete, finite loops woven into a network often called a spin foam. These loops represent the smallest possible units of space, a quantum of volume, meaning there is a limit to how small things can get, an idea that naturally avoids the troublesome singularities predicted by general relativity. In this theory, the Big Bang might not have been a singularity but a big bounce, a moment where a previous universe collapsed and then re-expanded into our own. While less popular in the public eye than string theory, loop quantum gravity offers a direct and compelling way to reconcile quantum mechanics with general relativity without requiring any hidden dimensions. Beyond these two giants, other inventive frameworks are also vying for attention. Causal dynamical triangulations takes a computational approach, building spacetime from the ground up out of simple, fundamental geometric building blocks, tiny triangles or tetrahedra. By allowing these pieces to connect following specific causal rules and using powerful computers to simulate their collective behavior, physicists have shown that a four-dimensional spacetime can indeed emerge naturally from the model, a fascinating result that suggests our experience of dimension and time may be a large-scale property of a deeper, more chaotic underlying reality. Another approach, called asymptotic safety, proposes that the problem with quantizing gravity might be solved if the strength of the gravitational force changes with energy scale in a very specific way, becoming finite and predictable at extremely high energies rather than spiraling into infinity. Each of these paths offers a unique perspective on the problem, reflecting the immense creativity and dedication of the theoretical physics community. The primary challenge facing all these theories is the same: a desperate lack of experimental data. The energy scales required to directly probe quantum gravity are unimaginably high, far beyond the reach of any particle collider we could ever hope to build. This forces physicists to become cosmic detectives, searching for indirect clues in the data we can collect. The ongoing observations of gravitational waves by LIGO and Virgo are a potential treasure trove. As these ripples in spacetime travel across the universe, subtle quantum gravitational effects might leave a tiny imprint on them, perhaps causing a slight dispersion where different frequencies travel at slightly different speeds. By analyzing these signals with exquisite precision, we might one day detect a signature that only one theory can explain. Similarly, the faint afterglow of the Big Bang, the cosmic microwave background, might hold frozen echoes of quantum gravitational processes from the universe's first instance. Certain patterns in its polarization could point toward specific models of inflation that are tied to grand unified theories or quantum gravity. Even precise measurements of the timing of light from distant pulsars could reveal minute evidence of a foamy spacetime structure at the smallest scales. Every new window we open onto the cosmos brings with it the hope that it might finally shed light on this deepest of mysteries. The reward for solving this puzzle would be nothing less than a complete transformation of our understanding of reality. A successful theory of quantum gravity would finally allow us to peer beyond the veil of the Big Bang and understand the true origin of our universe. It would reveal the fate of information that falls into a black hole, resolving the decades-old information paradox and telling us whether information is truly fundamental or can be lost forever. It could provide a definitive answer to the nature of dark energy and dark matter, perhaps showing they are manifestations of the underlying quantum structure of space-time. On a philosophical level, it would force us to reconsider the very nature of time and existence, potentially showing that time is not fundamental but emergent, a concept that arises from the quantum correlations between events. This isn't just abstract mathematics, it's a journey to the heart of what it means for anything to exist at all, a quest to uncover the ultimate rules that wrote the cosmos into being and continue to govern its every moment. To truly appreciate the story of our cosmic origins, we must first understand the profound evidence that anchors the Big Bang theory in reality. The most compelling clue comes from a faint, cold glow that permeates all of space, the cosmic microwave background radiation. Imagine turning on an old analog television to static. A small percentage of that snowy flicker is actually the remnant echo of the universe's fiery birth. This afterglow was first accidentally discovered in 1964 by Arno Penzias and Robert Wilson at Bell Labs, who were puzzled by a persistent, uniform microwave noise their giant horn antenna was picking up from every direction. They had stumbled upon the cooled-down light from a time, about 380,000 years after the Big Bang, when the universe had expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms. This event, known as recombination, allowed photons, which had been constantly scattering off charged particles, to finally travel freely across the cosmos. These same photons, stretched from visible light into microwaves by the expansion of the universe over billions of years, now bathe us in a thermal bath of just 2.725 degrees above absolute zero. The exquisite uniformity of this background, mapped in stunning detail by satellites like NAS, a Wilkinson microwave anisotropy probe, and the European Space Agency's Planck mission, provides a direct snapshot of the infant universe, confirming its hot, dense beginning. This cosmic fossil is not perfectly smooth, however. Embedded within it are tiny fluctuations in temperature, minute variations of about 1 part in 100,000. These anisotropies are the seeds of all future structure in the universe. They represent the slight over-densities and under-densities in the primordial plasma, the gravitational wells from which galaxies and galaxy clusters would eventually grow. The patterns in these fluctuations tell scientists precisely how much ordinary matter, dark matter, and dark energy the universe contains, and they provide a robust estimate of the universe's age, 13.8 billion years. This detailed map is a powerful confirmation of the Big Bang model, but it also points back to an even earlier, more mysterious epoch that set the stage for these initial conditions. The second pillar of evidence comes from the work of astronomer Edwin Hubble in the 1920s. By meticulously observing the light from distant galaxies, Hubble made a revolutionary discovery. Nearly all galaxies are moving away from us, and their speed is proportional to their distance. The farther away a galaxy is, the faster it is receding. This is not because we are at the center of some cosmic explosion. Rather, it is because space itself is expanding, carrying galaxies along with it like raisins in a rising loaf of raisin bread. This observation, now enshrined as Hubble's law, provides a direct and continuous record of the universe's expansion. By running the cosmic film backward, we are led inexorably to a moment when all the matter and energy in the observable universe was concentrated into an incredibly hot, dense point. While the Big Bang theory brilliantly describes the evolution of the universe from that first second onward, it leaves some of our most profound questions unanswered. The model is built upon Einstein's theory of general relativity, and at the moment of the Big Bang itself, the equations of relativity predict a singularity, a point of infinite density and temperature where the known laws of physics completely break down. This singularity represents a boundary, a hard limit to our current understanding. We cannot use our present tools to peer beyond it or to ask what caused it. The theory describes the expansion from that singularity but is silent on what, if anything, came before it or what triggered the initial expansion. This is where the theory of cosmic inflation proposed by Alan Guth and others provides a crucial extension, suggesting a period of exponential expansion that occurred in the first fraction of a second, smoothing out the universe and planting the seeds for galaxies. Yet even inflation typically requires some initial conditions to get started, pushing the ultimate question of origins back one step further. This leads to some of the most speculative and fascinating ideas in modern cosmology. Could our universe be part of a much larger, perhaps eternal, multiverse? Some theories suggest that our Big Bang was not a unique event but one of countless bubble universes continuously forming within a greater cosmic landscape. Another profound possibility is the concept of a cyclic universe where the cosmos undergoes an endless series of expansions and contractions, a series of Big Bangs and Big Crunches. In some of these models, like the one proposed by Roger Penrose, each cycle, or eon, is connected to the next, with the universe losing all information about its previous state in the transition. The idea of a universe with no absolute beginning is philosophically appealing to some, as it avoids the problem of a definitive creation event, but it remains highly speculative and difficult to test. The quest to understand our ultimate origins continues to drive the most advanced scientific missions. The Planck satellite's incredibly precise maps of the cosmic microwave background have not only confirmed the standard model of cosmology, but have also placed tight constraints on various inflationary models and even alternative theories. While no definitive evidence of a prior universe has been found, the search for unique imprints, such as concentric circles in the CMB that could be gravitational wave echoes from a previous eon, continues. Each new piece of data brings us closer to answering the timeless question of where everything came from, reminding us that the story of the Big Bang is not a finished book but a living, breathing narrative that we are still actively writing, one observation at a time. But if the very fabric of space-time can be warped by massive objects and probed by quantum particles, what about the space between them? What about the void itself? We often think of a vacuum as the very definition of nothingness, a completely empty, sterile void. But according to the bizarre and counterintuitive rules of quantum mechanics, nothing could be further from the truth. Empty space is not empty at all. It is a seething, bubbling, frenetic arena of activity, a quantum foam teeming with temporary particles and energy. This concept, known as vacuum energy, is one of the most well-established yet deeply puzzling ideas in all of modern physics, and it forces us to completely redefine what we mean by nothing. This bizarre behavior is a direct consequence of Werner Heisenberg's famous uncertainty principle, a cornerstone of quantum mechanics. This principle states that there is a fundamental limit to how precisely we can know certain pairs of properties, like a particle's energy and the time it possesses that energy. This isn't a limitation of our measuring equipment, it's a fundamental property of reality itself. On very short timescales, energy can fluctuate wildly, borrowing from the future to create something from nothing, as long as it pays that energy back almost instantly. This allows for the spontaneous creation of pairs of virtual particles, a particle and its antiparticle, that flash into existence for an unimaginably brief moment before annihilating each other and vanishing back into the vacuum. The entire universe is constantly filled with this ephemeral dance of creation and destruction, a quantum fireworks display happening all around us, in the space between stars and in the air between the atoms of your own body. It is the lowest energy state of a field, but it is far from calm and inert. We can actually observe the tangible effects of this quantum frenzy in a laboratory. The most famous demonstration is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum, separated by a gap smaller than the width of a human hair. Outside the plates, a whole spectrum of virtual particles of all different wavelengths can pop in and out of existence. But in the narrow gap between the plates, only virtual particles with wavelengths that fit perfectly between them can appear. This creates an imbalance in the quantum pressure, with more virtual particles pushing on the outside of the plates than on the inside. The plates experience a faint but measurable force pushing them together. This astonishing effect, first measured definitively in 1997, is a direct experimental confirmation that empty space is alive with quantum fluctuations. The void itself exerts a force. This leads us to one of the most embarrassing and profound problems in all of theoretical physics, a problem so severe it's often called the worst prediction in the history of science, the cosmological constant problem. When physicists attempt to calculate how much energy this endless creation and annihilation of virtual particles should contribute to the vacuum of space, they use the well-established rules of quantum field theory. They add up the contributions from all possible fields and all possible energy levels. The result is a number so catastrophically large it is almost incomprehensible. The calculated vacuum energy density should be around 120 orders of magnitude, that's a 1 with 120 zeros after it, greater than the value we actually observe from astronomical measurements. This discrepancy is not a small rounding error. It is larger than the difference between the size of a single proton and the entire observable universe. If the theoretical calculation were correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped apart every atom, every nucleus, in the infant universe before stars or galaxies could ever have formed. The fact that we exist at all is proof that this calculation is wildly, inexplicably wrong. This yawning chasm between theory and observation is the cosmological constant problem, and resolving it is one of the holy grails of modern physics. This problem is not just an academic curiosity. It sits at the very heart of one of the greatest mysteries in cosmology, the nature of dark energy. The observed acceleration of the universe's expansion, which we attribute to dark energy, requires a very specific, very small amount of energy density to be infused throughout the vacuum of space. This measured value is exactly in line with the value we get from astronomical observations, but it is a tiny, tiny fraction of the enormous value predicted by quantum field theory. So the puzzle is twofold. Why is the vacuum energy so small, and why does the small amount that remains have exactly the right value to cause the acceleration we see? It suggests that somehow the frenetic activity of the quantum vacuum almost completely cancels itself out, leaving behind only the faintest whisper of energy that we call dark energy. Understanding this cancellation mechanism would unlock the secrets of dark energy and the ultimate fate of the cosmos. Physicists have proposed several bold ideas to solve this monumental problem. One possibility is that we are missing a fundamental symmetry in nature, a new law of physics that would force the vacuum energy to be exactly zero. Another, even more radical idea invokes the multiverse. In the context of string theory's vast landscape of possible universes, the value of the vacuum energy might be different in each bubble universe. In the overwhelming majority of these universes, the vacuum energy would be enormous, and those universes would never develop any interesting structure. But in a rare few, by sheer random chance, the value would be small enough to allow galaxies and life to form. In this anthropic explanation, we find ourselves in such a universe not because it's special, but because it's one of the only types of universe we could possibly exist in. It's a controversial solution as it moves the question from physics to statistics, but it highlights the desperate creativity this problem inspires. Ultimately, the mystery of vacuum energy represents a fundamental clash between our two most successful theories, quantum mechanics and general relativity. Quantum field theory gives us a prediction for what the energy of empty space should be, and general relativity tells us how that energy should gravitate and influence the expansion of the universe. The fact that these two answers are irreconcilably different is the clearest possible signal that we are missing a deeper theory, a theory of quantum gravity that can seamlessly unite the world of the very small with the geometry of the very large. The hum of the quantum vacuum is a constant reminder that nothing is ever truly still, and that the greatest secrets of the cosmos are hidden not in the distant stars, but in the seemingly quiet void right in front of us. Yet even the most violent stellar death is dwarfed by a phenomenon so powerful it can outshine the combined light of every star in the universe, if only for a few fleeting seconds. Imagine an explosion so colossal that it unleashes in a single heartbeat more energy than our Sun will produce across its entire 10 billion-year lifespan. This is the staggering reality of a gamma-ray burst, the universe's most extreme and energetic class of cosmic explosion. These events are not merely spectacular. They are the death cries of massive stars and the collision songs of stellar corpses, cosmic beacons that illuminate the farthest reaches of space and time, revealing secrets about the most violent processes nature can concoct. The story of their discovery is a perfect example of scientific serendipity. In the late 1960s, during the height of the Cold War, the United States launched the Vela satellite series. Their sole purpose was to monitor the skies for the telltale gamma-ray signatures of clandestine nuclear weapons tests, ensuring compliance with the Nuclear Test Ban Treaty. But the satellites began detecting enormous bursts of gamma radiation that were clearly not coming from Earth. They were originating from deep space. Initially treated with utmost secrecy, this data eventually revealed a phenomenon entirely unknown to astronomy. These were not the acts of warring nations, but the distant, natural detonations of stars, a previously hidden aspect of the cosmos that was far more violent and energetic than anyone had ever imagined. It was a humbling reminder that the universe is full of surprises, often found when we are looking for something else entirely. As astronomers began to collect more data, a clear pattern emerged, leading to a fundamental classification of gamma-ray bursts based on their duration. The long-duration bursts, lasting more than 2 seconds and often for several minutes, are now understood to be associated with the death of the most massive stars in the universe. When a star many times more massive than our Sun exhausts its nuclear fuel, its core collapses catastrophically into a black hole. This is not a gentle surrender to gravity, it is a violent rebirth. In this process, powerful jets of plasma are launched from the poles of the nascent black hole, accelerated to nearly the speed of light by mechanisms we are still striving to understand. These jets, focused and deadly, punch their way through the outer layers of the dying star. If one of these narrowly focused beams happens to be pointed directly at Earth, we observe it as a long gamma-ray burst, a brilliant flash signaling the birth of a black hole and the death of a star. It is a stellar supernova on steroids, a hypernova, where the star doesn't just explode but is utterly torn apart by relativistic jets. In stark contrast are the short-duration bursts, lasting less than 2 seconds and often only a fraction of a second. For decades, their origin was a deeper mystery, as their brief nature made them incredibly difficult to locate and study. The breakthrough came with the ability to quickly pinpoint their locations and observe the aftermath. We now know that short GRBs are the signature of the most dense and violent mergers in the cosmos, the collision of two neutron stars or a neutron star and a black hole. When these incredibly massive objects spiral inward and finally merge, they create a newborn black hole surrounded by a torus of leftover neutron star material. In a fraction of a second, this system can launch its own incredibly powerful jets of gamma radiation. The confirmation of this theory was a landmark achievement in multi-messenger astronomy. The event known as GW 170817 was first detected by LIGO and Virgo as the gravitational waves from a neutron star merger. Within seconds, telescopes around the world swiveled to that patch of sky and witnessed the corresponding short gamma-ray burst and its brilliant afterglow, directly linking these fleeting flashes to the collision of stellar corpses. The burst of gamma rays itself is just the opening act. What follows is arguably just as important scientifically, the afterglow. As the relativistic jets plow into the surrounding interstellar gas, they create a shock wave that radiates across the entire electromagnetic spectrum, from X-rays to radio waves. This fading ember can be studied for days or even weeks, acting as a cosmic autopsy that reveals the energy of the explosion, the composition of the surrounding environment, and the distance to the event. It is through these afterglows that we can truly understand the physics powering these incredible explosions. They transform a mysterious, one-off flash into a rich, evolving story that astronomers can meticulously unpack. This ability to measure their distance has revealed one of the most profound applications of gamma-ray bursts. They are the ultimate deep space probes. Because they are so phenomenally bright, we can detect them from the very edge of the observable universe. Gamma-ray burst GRB 090423 was detected in 2009, and its light was measured to have been traveling for 13 billion years before reaching us. This means we are witnessing the death of a star that died when the universe was less than 600 million years old, a mere infant. By studying the light from these ancient explosions, we can probe the conditions in the earliest galaxies, understanding how quickly the first stars formed and died, and how they began to pollute the pristine cosmos with the first heavy elements necessary for planets and life. Furthermore, the vast distances involved allow us to conduct unique tests of the fundamental laws of physics. According to Einstein's theory of relativity, all light, regardless of its energy, should travel at the same speed in a vacuum. Some theories of quantum gravity, however, suggest that at extremely small scales, spacetime might have a foamy texture that could cause very high-energy gamma-ray photons to travel slightly slower than their lower-energy counterparts. By carefully analyzing the arrival times of photons of different energies from a gamma-ray burst that has traveled across billions of light-years, scientists can hunt for this tiny delay. So far, no such effect has been found, placing important constraints on theories that attempt to unify gravity and quantum mechanics. In this way, these cosmic explosions become natural laboratories for testing the very fabric of reality itself. Now, let's shift our focus from the explosive death of stars to a missing piece in the very fabric of reality: a theoretical phantom that has eluded physicists for over a century. Every magnet you've ever held, from a simple refrigerator decoration to the complex one in a speaker, has two poles, a north and a south. If you break a bar magnet in half, you don't isolate a single pole. You simply create two new, smaller magnets, each with its own north and south. This is a fundamental rule of electromagnetism as we understand it. But what if that wasn't the whole story? Imagine a particle that was the magnetic equivalent of an electron, a particle with just a north pole or just a south pole with no opposite counterpart. This hypothetical entity is known as a magnetic monopole, and its potential existence isn't just a curiosity. It would force a profound rewrite of our understanding of the universe's most fundamental forces. The case for monopoles isn't born from whimsy but from a deep sense of mathematical symmetry. Our current theories of electromagnetism, encapsulated in James Clerk Maxwell's famous equations, are beautifully symmetric between electricity and magnetism, but with one glaring exception. Electric charges exist as isolated positive or negative particles like protons and electrons, but there are no corresponding isolated magnetic charges. This asymmetry has long bothered physicists, who often find that nature prefers elegant symmetry. The drive to unify the fundamental forces provides an even stronger argument. Grand unified theories, which attempt to describe the electromagnetic, weak, and strong nuclear forces as a single force that existed in the extreme energy of the early universe, almost universally predict the existence of magnetic monopoles. In these models, monopoles aren't just possible, they are inevitable. They would be incredibly massive, stable particles, relics from a time when the cosmos was 1 trillion times hotter than the core of our sun, and the forces of nature were indistinguishable from one another. This leads us to a major cosmological puzzle known as the monopole problem. If grand unified theories are correct, the phase transition as the universe cooled and the forces separated from their unified state should have produced a staggering number of these magnetic monopoles. They would be as abundant as protons, meaning there should be at least one in every liter of space in the universe. Their immense mass would dominate the density of the cosmos, and we would be swimming in them. Yet, despite decades of searching, not a single confirmed magnetic monopole has ever been detected. Their absence is a glaring contradiction between elegant theory and observable reality. This crisis was a primary motivator for the development of the theory of cosmic inflation. The idea that the universe underwent a period of exponential expansion in its first moments provides an elegant solution. This incredible stretching of spacetime would have diluted the density of any primordial monopoles to virtually zero, sweeping them so far beyond our observable horizon that finding one becomes extraordinarily unlikely. The fact that we don't see monopoles is actually a key piece of evidence that something like inflation must have occurred. The discovery of a magnetic monopole would be a scientific earthquake of unprecedented magnitude. First and foremost, it would provide the first direct experimental evidence for physics beyond the standard model, confirming the core ideas of grand unified theories and giving us a direct window into the universe when it was just a fraction of a second old. It would also elegantly explain a long-standing mystery, the quantization of electric charge. Why is the charge of an electron exactly equal and opposite to that of a proton? Why do all observed particles carry charges that are integer multiples of this fundamental unit? The existence of even a single magnetic monopole would provide a natural explanation for this phenomenon, as the laws of quantum mechanics would then require all electric charges to be quantized. It would complete the beautiful symmetry between electricity and magnetism that Maxwell first envisioned, finally placing them on an equal footing. The hunt for these elusive particles is a testament to scientific perseverance. Experiments have searched for them everywhere, in moon rocks and oceanic crust, in ancient mica crystals that could have trapped them long ago, and even using entire particle detectors as giant monopole traps. Current efforts like the Monopole and Exotics detector at the LHC or Mo-Edel experiment at CERN are specifically designed to be sensitive to these highly ionizing particles. They use stacks of plastic detectors that will be permanently damaged by the passage of a massive monopole, leaving a telltale etch that could be analyzed long after a collision event. While the Large Hadron Collider smashes protons together at unprecedented energies, briefly recreating conditions not seen since the Big Bang, it could potentially produce a monopole-antimonopole pair, offering a chance to create and study one in a controlled environment for the first time. The ongoing search for magnetic monopoles is far more than a technical exercise. It is a fundamental inquiry into the symmetry of the cosmos. It asks whether the universe at its deepest level is built on a foundation of perfect mathematical balance, and whether the forces that govern everything from atoms to galaxies are truly unified. Finding one would be a discovery on par with the identification of the electron or the detection of the Higgs boson, a moment that would instantly transform a cornerstone of theoretical physics into observable reality and open a new chapter in our understanding of matter, energy, and the very origin of everything. After decades of planning and technical challenges, the James Webb Space Telescope represents a quantum leap in our ability to interrogate the cosmos, a masterpiece of engineering now perched 1 million miles from Earth at the gravitationally stable Lagrange point 2. Unlike its predecessor, the Hubble Space Telescope, which primarily observes visible and ultraviolet light, Webb is an infrared telescope, a design choice that fundamentally changes what we can see. Infrared light has longer wavelengths than visible light, allowing it to pass through vast clouds of interstellar dust that would otherwise obscure our view. More importantly, due to the relentless expansion of the universe, the light from the very first stars and galaxies has been stretched or redshifted from visible wavelengths into the infrared part of the spectrum. For Hubble, these ancient objects were invisible, but for Webb, they are perfectly tuned to its instruments, making it nothing less than a time machine capable of directly witnessing the cosmic dawn. The heart of this revolutionary observatory is its suite of 4 powerful instruments, each designed for a specific and profound task. The Near-Infrared Camera, or NIRCam, is Webb's primary imager, responsible for those stunning, deep-field photographs that reveal countless galaxies sparkling like diamonds on black velvet. But its work goes far beyond pretty pictures. NIRCam is tasked with detecting the faintest infrared glow from the universe's earliest stellar populations. Then there's the Near-Infrared Spectrograph, NIRSpec, a truly remarkable instrument capable of observing up to 100 objects simultaneously. Using a complex microshutter array, it can open tiny windows to the light of individual galaxies in a crowded field, allowing scientists to analyze their chemical composition and distance at an unprecedented scale, effectively taking the cosmic census of the infant universe. To peer into the densest stellar nurseries and the dusty disks where planets are born, Webb employs the mid-infrared instrument MIRI. Operating at the coldest temperatures, MIRI sees the heat signatures of cool objects, revealing the structures of protoplanetary disks and the atmospheres of exoplanets in incredible detail. Finally, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph provides exceptional pointing stability and is particularly adept at hunting for exoplanets by precisely measuring the slight dimming of a star as a planet transits across its face. Some of Webb's most startling early results have come from its deep field observations, which have consistently revealed a surprising abundance of fully formed, massive galaxies at redshifts far greater than most cosmological models predicted. Scientists expected to see small, fragile, infant galaxies slowly merging together in the early universe, but instead, Webb found mature, structured galaxies similar to our own Milky Way, existing at a time when the universe was only a few 100 million years old. This discovery presents a significant challenge to our current understanding of galaxy formation and dark matter's role in the process. It suggests that the early universe was able to assemble complex structures much faster and more efficiently than anyone had theorized, forcing a major re-evaluation of our cosmic timelines and potentially pointing toward new physics governing the behavior of dark matter and the initial conditions set by inflation. Perhaps the most publicly captivating aspect of Webb's mission is its ability to characterize the atmospheres of planets orbiting other stars. When an exoplanet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Webb's sensitive spectrographs can dissect this light, looking for the unique chemical fingerprints of specific molecules that absorb light at characteristic wavelengths. This turns the telescope into a remote chemical laboratory, capable of identifying gases like water vapor, methane, carbon dioxide, and even oxygen from light years away. A prime target is the TRAPPIST-1 system, a red dwarf star with 7 Earth-sized planets, several of which orbit within the habitable zone. Webb has already begun analyzing the atmospheres of these worlds, and while the initial data suggests some may lack the thick atmospheres necessary for life as we know it, the search is ongoing. The ultimate goal is to find a planet with an atmosphere that is not only life-friendly but shows a chemical imbalance such as the simultaneous presence of oxygen and methane. That could be a strong, albeit indirect, signature of biological activity. Webb's infrared vision is also peeling back the veils on the life cycles of stars and planets, allowing us to witness their birth in unprecedented detail. By staring into dense molecular clouds, the cosmic nurseries of the universe, Webb can see through the obscuring dust to watch protostars igniting and, crucially, to study the intricate structures of the protoplanetary disks swirling around them. In these disks, planets are in the process of assembly, and Webb's spectroscopy can identify the building blocks, detecting water ice, silicates, and complex organic molecules that will eventually become part of new planetary systems. This provides a direct link between the raw materials available in a young system and the types of planets that form, helping us understand the conditions that led to our own solar system's architecture and the prevalence of habitable worlds across the galaxy. The telescope's contributions extend to the most extreme objects in the universe as well. By observing the region around Sagittarius, a star, the supermassive black hole at the center of our galaxy, Webb provides complementary data to the Event Horizon Telescope, helping to characterize the accretion flow and high-energy processes at work. It can also study the powerful outflows from quasars and active galactic nuclei, measuring how these tremendous eruptions influence star formation in their host galaxies and contribute to the feedback cycles that regulate galactic evolution. Furthermore, by observing how the gravity of massive galaxy clusters warps the light from more distant background galaxies, a phenomenon known as gravitational lensing, Webb is creating detailed maps of the distribution of both visible and dark matter, offering new clues to the mysterious substance that forms the cosmic web. Each observation, from the first glimmers of starlight to the chemistry of alien worlds, is weaving together a more complete and astonishing picture of our dynamic and evolving universe. But this profound observation leads us to a much deeper and more philosophical question. Why is the universe so exquisitely calibrated for our existence? This puzzle is known as the fine-tuning problem, and it pushes us to the very boundaries of science, philosophy, and even theology. To grapple with it, scientists and thinkers have developed a framework known as the anthropic principle. In its simplest, most observational form, the weak anthropic principle states that the universe we observe must be compatible with the conscious life that observes it. It's a statement of selection bias. We shouldn't be surprised to find ourselves in a universe that allows for our existence, because we couldn't possibly find ourselves in one that doesn't. It doesn't explain why such a universe exists. It simply notes that our presence as observers necessarily filters the kind of universe we can perceive. This is the most scientifically conservative interpretation, a simple acknowledgement of our own place in the cosmic order. A much stronger and more controversial version, the strong anthropic principle, makes a far more audacious claim. It suggests that the universe must have properties that allow life to develop within it at some stage in its history. This statement moves from observation to a kind of necessity, implying that the laws of physics are somehow constrained or required to produce conscious observers. This stronger version often veers into metaphysical territory, with some interpretations suggesting the laws of nature are not accidental but almost purposeful, a notion that resonates with ideas of design or a deeper, underlying teleology in the cosmos. The distinction between the weak and strong principles is crucial. One is a logical statement about our perspective, while the other is a claim about the fundamental nature of the universe itself. The fine-tuning argument gains its power from specific, jaw-dropping examples. Consider the strength of the fundamental forces. The strong nuclear force that binds atomic nuclei together is perfectly balanced. If it were just a few percent stronger, hydrogen would be unstable and stars could not form. If it were slightly weaker, complex elements necessary for life would never be forged in stellar furnaces. The cosmological constant, which governs the energy density of empty space and the acceleration of the universe's expansion, is perhaps the most famous example. The value we measure is astonishingly small, but if it were even slightly larger by just 1 part in 10 to the power of 120, the universe would have expanded so rapidly that no galaxies, stars, or planets could ever have coalesced. The list goes on. The exact mass of the neutron, the precise ratio of the gravitational constant to the electromagnetic force. Tweak any of these values by a hair, and the universe becomes a lifeless void, either a chaotic plasma, a frigid expanse of scattered particles, or collapsed back into a black hole long ago. This incredible precision inevitably leads to a profound debate between chance and design. One perspective posits that this fine-tuning is evidence of a cosmic designer, an intelligence that set the dials to their life-permitting values. This argument, often called the teleological argument, has been updated for the modern scientific age, moving from the observation of complex life to the underlying laws that make complexity possible. Critics, however, point out that this explanation simply pushes the question back a step: who designed the designer, and resides outside the realm of scientific testability. The alternative is to accept an almost miraculous coincidence, a universe that won the cosmic lottery against inconceivable odds purely by random chance. For many scientists, this is deeply unsatisfying, as it asks us to accept a statistical near impossibility as the foundation of our existence. There is, however, a third way, a scientific framework that has gained significant traction as a potential solution: the multiverse. If our universe is just one bubble in a vast, perhaps infinite, cosmic foam of universes, each with its own random set of physical constants and laws, then the fine-tuning problem evaporates. In such a multiverse, spawned by eternal inflation or string theory's landscape of possibilities, the vast majority of universes would be stillborn or barren. their laws incapable of supporting any form of complex structure. But in a tiny, tiny fraction of them, the numbers would, by pure chance, line up correctly. We find ourselves in one of those rare, life-friendly universes not because it was designed for us, but because we are a product of its friendly conditions. In this view, the anthropic principle becomes a selection effect within a vast ensemble. We don't see the countless dead universes, we only see the one that allowed us to see it. It's a breathtakingly vast and humbling concept that exchanges a universe fine-tuned for life with a life that has found itself in one of the very few universes that could possibly host it. This discussion inevitably spills over from the halls of physics into the domains of philosophy and theology, forcing us to confront what we mean by explanation itself. Is the multiverse a legitimate scientific solution, or is it an untestable metaphysical speculation that simply moves the mystery to a larger scale? Can we ever hope to gather evidence for other universes, or will they forever remain beyond our empirical grasp? The anthropic principle, in all its forms, challenges the traditional boundaries of scientific inquiry. It reminds us that the act of observation is not a passive process, but is inextricably linked to the reality being observed. Our very existence is a data point that must be accounted for in any complete theory of the cosmos. Whether seen as a profound clue pointing toward a deeper multiversal reality, a modern scientific argument for purpose, or simply a logical tautology, the fine-tuning of the universe remains one of the most provocative and enduring mysteries, compelling us to wonder not just how the universe is, but why it is the way it is. Yet as compelling as this idea may be, the hunt for these ancient relics has proven to be incredibly difficult, forcing scientists to become cosmic detectives searching for subtle clues. The primary method for looking for primordial black holes has been through a phenomenon called gravitational microlensing. The principle is straightforward. If a compact, dark object like a primordial black hole were to pass directly between Earth and a distant star, its gravity would act like a lens, bending and focusing the star's light. From our perspective, the star would temporarily appear to brighten, then fade back to normal as the object moves on. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, projects like the Optical Gravitational Lensing Experiment, or OGLE, have scanned the skies for these telltale flashes. The results have placed severe constraints on the idea. While a population of planet mass or asteroid mass black holes can't be entirely ruled out, these surveys have largely excluded the possibility that such objects make up a significant fraction of the dark matter in the halo of our galaxy. The simple fact is, we just haven't seen enough of these microlensing events to account for the vast amount of dark matter we know must be there. The dawn of gravitational wave astronomy has opened up an entirely new front in this investigation, offering a different way to weigh the evidence. The groundbreaking detections by LIGO and Virgo of merging black holes have provided a fresh and exciting perspective. Some of the black holes involved in these collisions have been measured at masses that are somewhat unusual heavier than what is typically expected from the collapse of massive stars. This unexpected mass range has reignited the conversation about a primordial origin. Could these be ancient black holes forged in the first second of the universe, now finally finding each other and merging after billions of years? It's a tantalizing possibility, but it's not the only explanation. Astrophysicists have also developed models showing how stellar mass black holes could grow to these sizes through successive mergers or by consuming gas in dense environments. The gravitational wave data doesn't yet provide a smoking gun, but it has undoubtedly brought the idea back into the scientific mainstream, forcing researchers to consider all possibilities for how black holes of various sizes can form. Beyond simply accounting for dark matter, the existence of primordial black holes would have profound and sweeping implications for other cosmic puzzles. One of the biggest mysteries in astronomy is the origin of supermassive black holes, the monsters weighing millions or billions of times the mass of our Sun that lurk at the centers of most galaxies. These behemoths appear to have existed when the universe was very young, which is a problem for traditional models. It's difficult to understand how a regular stellar mass black hole could have grown so massive so quickly. Primordial black holes offer an elegant solution. They could have served as ready-made seeds. A few unusually large primordial black holes, formed with a head start of perhaps 1,000 solar masses, would have had plenty of time to gorge on gas and merge with others, rapidly growing into the supermassive black holes we observe in the early universe. In this scenario, the giants at the centers of galaxies wouldn't have had to start from scratch. They would have been planted as seeds in the fertile soil of the young cosmos. The potential influence of these objects might even extend to the very smallest scales of the solar system. Some theorists have proposed that a small, asteroid-mass primordial black hole could potentially be captured by a star like our Sun, ending up in a wide, distant orbit. If such an object were out there in the far reaches of our own solar system, it could exert a gravitational influence on the icy bodies in the Kuiper belt, potentially explaining some of the strange orbital clustering that has led to the hypothesis of a Planet 9. While a primordial black hole is a far more exotic explanation than an undiscovered planet, it's a fascinating example of how this idea could reach into unexpected areas of astronomy, connecting the largest cosmological questions to the dynamics of our own celestial neighborhood. Ultimately, the quest to find primordial black holes is about more than just identifying one component of dark matter. It's a direct test of the physics of the very early universe. Confirming their existence would provide a unique window into a period of time we can never recreate, revealing the nature of the density fluctuations that emerged from the Big Bang. It would tell us that the infant universe was capable of far wilder and more violent extremes than we currently understand. The search continues with ever more inventive methods, from looking for the telltale flashes when a tiny black hole evaporates in a final burst of Hawking radiation, to searching for the distinct gravitational wave background that a large population of them would create. While the evidence remains elusive, the pursuit itself pushes the boundaries of cosmology, reminding us that the dark matter problem may still have a solution that is stranger and more wonderful than we have yet dared to imagine. For decades, astronomers have operated under a simple assumption that the expansion of the universe is the dominant motion, carrying all galaxies apart from one another in a smooth, predictable flow. But in the 1970s, a team of scientists, including the renowned astronomer Sandra Faber, began to notice something deeply strange. By carefully measuring the redshifts of galaxies, they could calculate how fast they should be receding from us due to the cosmic expansion. However, when they compared these predictions to the actual observed velocities, they found a significant discrepancy. Our own Milky Way galaxy, along with our entire local group of galaxies, was caught in a vast, mysterious river of motion, deviating from the universal expansion by hundreds of kilometers per second. We were not simply drifting apart, we were all being pulled en masse toward a specific point in the sky, a region in the direction of the southern constellations of Centaurus and Hydra. This unseen source of immense gravitational influence was dubbed the Great Attractor, and it has captivated cosmologists ever since as one of the most intriguing large-scale mysteries in the cosmos. The primary challenge in solving this mystery was a classic case of cosmic irony. The very thing we wanted to study was hidden behind our own line of sight. The direction of the Great Attractor lies in what astronomers call the zone of avoidance, a region of the sky obscured by the thick dust, gas, and countless stars of the Milky Way's galactic plane. It's like trying to identify a magnificent mountain range on the horizon while standing in a dense, foggy forest. Our own galaxy was blocking the view. For years, the true nature of the Great Attractor remained shrouded in this literal cosmic dust, its immense gravitational pull evident only through its effects on the motion of thousands of galaxies, including our own. The breakthrough came with the advent of infrared astronomy. Infrared light, with its longer wavelengths, can pierce through the interstellar dust that scatters visible light. Space telescopes like the Infrared Astronomical Satellite, or IRAS, and later NASA Spitzer Space Telescope, were able to peer through the galactic veil and finally map what lay in this forbidden zone. What they revealed was astonishing. The heart of the Great Attractor was not a single, impossibly massive object, but an enormous confluence of matter, a massive galaxy cluster known as the Norma Cluster, surrounded by a dense web of other galaxies and vast clouds of dark matter. This region, now called the Norma Supercluster, is an immense gravitational well, a concentration of mass so great that it dominates the motion of galaxies across an enormous volume of space. The pull we feel is the collective gravity of this entire dense knot in the cosmic web. Yet the story grew even larger. The discovery of the Great Attractor and the Norma Supercluster turned out to be just one piece of a far grander cosmic structure. In 2014, an international team of astronomers led by R. Brent Tully announced the definition of a supercluster on a scale previously unappreciated. They named it Laniakea, a Hawaiian word meaning immense heavens. Using a novel technique to map the peculiar velocities of thousands of galaxies, they were able to trace the gravitational watershed of the cosmos. Laniakea is not defined by a dense concentration of galaxies but by the boundaries of their motion, the points at which the flow of galaxies diverges toward different gravitational centers. This colossal structure is over 500 million light-years across and contains the mass of 100 quadrillion suns. It encompasses our own local group, the Virgo supercluster, the Norma supercluster which powers the Great Attractor, and thousands of other galaxies, all flowing together in a single, gravitationally bound river of stars and dark matter toward a central point near the Norma cluster. This revelation fundamentally changes our understanding of the universe's architecture. It shows us that the cosmos is organized in a hierarchical fashion, with galaxies forming groups, which gather into clusters, which are embedded within superclusters like Laniakea, which themselves may be part of even larger filaments and walls in the cosmic web. The Great Attractor is not a destination but a gravitational waypoint, a major hub in this vast network. The motion it imparts is a direct testament to the overwhelming influence of dark matter, the invisible scaffolding that makes up the bulk of the universe's mass. It is the gravitational pull from the dark matter associated with these immense structures that shapes these large-scale flows, guiding the paths of galaxies across billions of years. Understanding these motions is crucial because they allow us to map the distribution of all matter, both seen and unseen, in a way that simply counting visible galaxies cannot. By studying the peculiar velocities of galaxies, how they deviate from the smooth Hubble flow cosmologists can create a dynamic map of the cosmos's mass. This helps us to better understand the properties of dark matter and the initial conditions that gave rise to such vast structures from the nearly uniform early universe. The Great Attractor and our journey within the Laniakea supercluster are a powerful reminder that our place in the universe is not static. We are part of a grand gravitational dance, flowing along currents set in motion by the hidden architecture of the cosmos itself. Now let's venture into one of the most speculative and mind-bending ideas in all of theoretical physics, a concept that seems to tear up the fundamental rulebook of the universe. According to Einstein's special theory of relativity, the speed of light in a vacuum is the universe's ultimate speed limit. It's a cosmic traffic law that nothing with mass can ever accelerate to reach this speed, let alone exceed it. But what if there was a class of particles that didn't need to accelerate to reach light speed? What if they were born already moving faster than light and could never slow down to that universal limit? This is the wild and controversial hypothesis of tachyons, a name derived from the Greek word tachys, meaning swift. These are not particles that accelerate beyond light speed. They are hypothetical entities for which a velocity greater than light is their natural, permanent state of being, much like how we are forever bound to velocities below light speed. The most startling property of a tachyon isn't its speed, but what that speed implies about its mass. In the equations of special relativity, as an object with real mass approaches the speed of light, its energy requirements skyrocket towards infinity, making it impossible to actually reach that velocity. For a tachyon, the mathematics flips this concept on its head. To consistently exist faster than light, a tachyon would need to possess what physicists call an imaginary mass. This doesn't mean a mass that you simply imagine in your head. It's a specific mathematical term. Imaginary mass is a number that, when squared, gives a negative result. This bizarre property is the key that theoretically unlocks the door to superluminal travel in the equations, but it also leads to some profoundly strange and troubling consequences that most physicists find deeply unpalatable. The most serious objection to tachyons is not their weird mass, but the catastrophic damage their existence would do to our understanding of cause and effect. The principle of causality, that a cause must always precede its effect, is a foundational pillar not just of physics, but of reality as we experience it. If tachyons could be used to send information faster than light, this principle shatters. Imagine a scenario where you use a tachyon beam to send a message to a distant star system. In some reference frames, thanks to the relativity of simultaneity, that message could be received before it was even sent. This opens the door to infamous paradoxes, like the grandfather paradox, where you could potentially send a signal back in time to prevent your own birth. Most physicists argue that this alone makes tachyons impossible, as nature likely has built-in mechanisms to prevent such logical inconsistencies and preserve a stable, paradox-free timeline. The mathematics might allow for a solution, but the physics of a sensible universe likely does not. Despite these monumental problems, the idea of tachyons hasn't been completely abandoned by serious science. They occasionally appear in highly abstract discussions within quantum field theory, not as real particles we might detect, but as theoretical tools. In some complex models, the appearance of a tachyon in the equations is not seen as evidence of faster-than-light matter, but rather as a signal that the system being described is in an unstable state. It indicates that the vacuum, the lowest energy state of a field, is not truly stable and needs to settle into a different, more stable configuration. This is how the Higgs mechanism, which gives other particles their mass, was initially theorized. The Higgs field was once described as having a tachyonic nature, but this was a mathematical indication that the universe's vacuum was in a false state, and the field needed to condense into its true, stable state, a process that subsequently bestowed mass upon particles. In this context, the tachyon is not a particle but a signpost pointing toward a deeper physical process. It is in the realm of science fiction, however, that tachyons have truly found a home, free from the constraints of causal paradoxes. They are a beloved staple, often used as a convenient plot device to explain everything from instant communication across galactic distances to time travel itself. From Star Trek to countless novels, tachyons are the go-to technobabble for breaking the light barrier. This popularity speaks to a deep human fascination with overcoming limits, but it has also created a wide gap between their portrayal in fiction and their dubious status in actual physics. While they capture our imagination, they remain firmly in the category of mathematical curiosities rather than serious candidates for real particles. So, if they are so problematic, why do physicists still occasionally entertain the thought? The value of a concept like the tachyon lies in its ability to push our theories to the absolute breaking point. By exploring the farthest edges of what our equations might allow, even if it leads to apparent nonsense, we stress test the foundations of our knowledge. It forces us to ask why certain rules, like the speed of light limit, must exist. Is it merely a property of the spacetime we inhabit, or is it a fundamental requirement for a logical, consistent universe where the past stays in the past and the future remains unknown? The continued discussion around tachyons, however speculative, is a testament to our desire to understand not just how the universe works, but why it works that way, probing the very boundaries of possibility to see if they just might, bend. Picture this: it's a warm summer night in Delaware, Ohio, August 15, 1977. Jerry Amon, a volunteer researcher for Ohio State University's Big Ear radio telescope, is sifting through reams of computer printout data from the previous few days. The telescope is methodically scanning the sky as part of the Search for Extraterrestrial Intelligence, or SETI, program, listening for any radio signal that stands out from the natural background static of the cosmos. As his eyes scan down the page, a sequence of alphanumeric characters jumps out at him, 6 letters and numbers so unexpected, so statistically outrageous that he circles them in red pen and simply writes beside them, "Wow." That single, electrifying exclamation would give this signal its famous name and cement its place as the most tantalizing, unexplained event in the history of the search for alien life. The data itself was as clean and perfect as a signal could possibly be. It was a strong, narrowband radio blast at precisely 1420 MHz, a frequency that sits in a protected band of the spectrum where natural cosmic sources are forbidden to broadcast. This is the emission frequency of hydrogen, the most common element in the universe, a logical choice for any civilization trying to send a beacon saying, "We are here." The signal lasted for a full 72 seconds, which is exactly how long the Big Ear telescope's fixed receiver would have taken to sweep across a single point in the sky. It rose in intensity as the telescope moved into it, peaked, and then faded away perfectly, creating a perfect bell curve on the printout. It had all the hallmarks of an artificial interstellar broadcast. Yet, despite decades of relentless searching by countless telescopes aimed at that same patch of sky near the star group Chi Sagittarii in the constellation Sagittarius, the signal never repeated. Not once. It was a one-time cosmic shout that vanished as mysteriously as it appeared, leaving behind only a circled code on a faded piece of paper and a mountain of questions. This singular event perfectly encapsulates the immense challenge and profound frustration of SETI. The universe is filled with a deafening cacophony of natural radio noise, the hiss of pulsars, the crackle of distant quasars, the microwave afterglow of the Big Bang itself. Finding a genuine technosignature, a signal clearly engineered by intelligence, is like trying to hear a single, whispered word across a crowded, roaring stadium during a thunderstorm. The wow signal was that perfect whisper, heard for just a moment in a lull in the noise, but without a repeat performance, it remains an anecdote, a ghost that scientists can neither confirm nor dismiss. It highlights the needle in a haystack nature of the work. where researchers must sift through millions of false alarms caused by earthly interference from satellites, radar, and even microwave ovens to find that 1 in a billion anomaly that might be real. In the wake of the WOW signal, the search has evolved from single telescopes like Big Ear to coordinated, powerful global efforts. Projects like Breakthrough Listen, funded by billionaire Yuri Milner, represent the new frontier. This initiative uses some of the world's most powerful radio telescopes, like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to scan millions of stars and hundreds of nearby galaxies. Their approach is vastly more sophisticated, using advanced algorithms to analyze mind-boggling amounts of data in real time, filtering out interference and searching for signals that are not just narrowband but also exhibit other signs of artificiality, like drifting in frequency or being pulsed in a pattern. They are listening for the cosmic equivalent of a perfectly tuned, sustained musical note amidst the random noise of a forest. So what could have caused the WOW signal if it wasn't aliens? Astronomers have proposed several natural explanations, though each has its own shortcomings. Could it have been a comet? Some have suggested that the hydrogen clouds surrounding comets could emit a similar signal, but no known comets were in that region of the sky at that time. Could it have been a brief, never-before-seen astrophysical transient, a one-off stellar burp, or a peculiar form of interstellar scintillation that focused a weak signal into a powerful spike? Possibly, but such events are theorized to be incredibly rare, and the perfect, artificial-looking characteristics of the signal make it a stubborn outlier. The most prosaic explanation is that it was reflected space debris or a secret military satellite transmission, but the specific frequency and the fact it was never heard again make even this unlikely. Its origin remains an open case, a mystery that continues to defy a simple solution. Ultimately, the enduring legacy of the WOW signal is not as evidence of aliens, but as a symbol of hope and a catalyst for curiosity. It is a reminder that the universe is vast and full of surprises, and that the possibility of discovery is always just one observation away. It fuels the passion of scientists and the public alike, driving the development of more sensitive technology and more clever methods of analysis. That one circled word on a printout is a testament to the human spirit's unwavering desire to answer the most profound question we can ask: are we alone? It is a question that continues to echo unanswered into the silent depths of space, urging us to keep listening. Take a moment to step outside on a clear, moonless night and look up. The sky is a breathtaking tapestry of stars, a scene of profound and majestic darkness punctuated by countless points of light. It is a view we are so familiar with that we rarely stop to consider how truly strange it is. In the early 19th century, the German astronomer Heinrich Wilhelm Olbers formulated a paradox that highlights this very strangeness, and it asks a deceptively simple question. If the universe is infinite, static, and filled with an endless number of stars, why is the night sky dark? Why isn't every single point in the heavens blazing with the light of a star? Think of it like this. In an infinite forest, no matter which direction you look, your line of sight will eventually land on a tree. By the same logic, in an infinite universe, every line of sight from Earth should eventually terminate at the surface of a star, making the entire night sky as brilliantly, uniformly bright as the surface of the sun. The fact that it is not, that we are surrounded by darkness, is one of the most important clues we have about the true nature of the cosmos. The resolution to Olbers' paradox is not one single answer, but a powerful combination of two fundamental truths about our universe, both of which were completely unknown in Olbers' time. The first and most crucial is that the universe is not infinitely old. It has a definite beginning. The Big Bang occurred roughly 13.8 billion years ago, which means that light has had only 13.8 billion years to travel across space. Even if the universe is infinite in size, we can only see the light from stars and galaxies that lies within a sphere centered on us with a radius of 13.8 billion light-years, a boundary we call the observable universe. There are stars and galaxies beyond this cosmic horizon, but their light simply hasn't had enough time to reach us yet. The second key is that the universe is not static, it is dynamically expanding. This expansion stretches the very fabric of space, and as it does so, it stretches the wavelengths of light traveling through it, shifting them toward the red end of the spectrum. This phenomenon, known as cosmological redshift, saps the energy of photons from the most distant galaxies. The light that does manage to reach us from the far reaches of the cosmos is thus rendered faint and shifted into invisible infrared wavelengths, its energy diluted by the relentless expansion of space itself. The darkness between the stars is not an emptiness, but a record of light that is too young, too stretched, and too feeble to fill our eyes. This elegant solution connects directly to another profound piece of our cosmic history, the cosmic microwave background radiation. That faint, cold glow that permeates all of space is, in a very real sense, the ultimate answer to Olber's paradox. It is the light from the early universe, once blindingly bright, that has been so dramatically redshifted by expansion over billions of years that it has cooled from visible light into microwaves. We are, in effect, living inside the cooled embers of the primordial fireball. If the universe were static and eternal, this background glow would not be a cold whisper. It would be an intense, searing heat that would vaporize all matter. The fact that we detect it as a cold microwave signal is definitive proof that the universe had a hot, dense beginning and has been expanding and cooling ever since. The darkness of the night sky, therefore, is not a void but a positive piece of evidence. It is the signature of a cosmos with a finite age and a dynamic nature, a universe that is actively evolving and telling the story of its own origin in the silent language of absent light. But to truly grasp the sheer strangeness of quantum foam, we need to venture down to the smallest possible scale nature allows, the Planck length. This is not just small, it is the ultimate basement of reality, a distance of about 10 to the negative 35 meters. To put that in perspective, if you were to magnify a single atom to the size of the entire observable universe, the Planck length would be roughly the height of an average tree. At this unimaginably tiny scale, the smooth, warped fabric of spacetime described by Einstein's general relativity is no longer a valid picture. The uncertainty principle ensures that the energy fields that make up spacetime itself are in a state of violent, unpredictable fluctuation. It's as if the calm, rolling ocean of spacetime, when viewed with a powerful enough microscope, reveals itself to be a seething, bubbling foam. This isn't just empty space. It is a dynamic, chaotic medium where the very concepts of here and there or now and then begin to lose all meaning. This radical idea was first proposed by the brilliant physicist John Wheeler in the 1950s, a mind that was never afraid to venture into the wildest frontiers of theoretical physics. Wheeler realized that if you applied the core principles of quantum mechanics not just to particles moving through space, but to the geometry of spacetime itself, you would get this foamy, turbulent structure. In the quantum foam, the smooth, continuous stage of the universe is replaced by a chaotic soup where tiny wormholes might spontaneously form, connecting different points in space for an infinitesimally short time, and virtual black holes could blink into and out of existence. These aren't stable structures you could travel through or fall into. They are ephemeral quantum fluctuations, the space-time equivalent of the virtual particles that pop in and out of the vacuum. Wheeler's profound insight was that the smooth, predictable universe we experience is merely an average, a large-scale illusion that emerges from this underlying quantum frenzy, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. The potential implications of this foamy texture for the behavior of matter and information are staggering. Imagine a single photon, a particle of light, traveling across billions of light years from a distant quasar. According to our classical view, it travels in a perfectly straight line through smooth spacetime. But if spacetime is foamy at the Planck scale, that photon's path isn't straight at all. It's constantly being jostled and buffeted by the turbulent foam, taking a slightly zig-zagging route. For a single photon, this effect is utterly negligible. But over an immense distance, these tiny deviations could add up, causing photons of different energies to travel at very slightly different speeds. A higher energy photon with a smaller wavelength might interact more frequently with the foam's tiny structure, potentially making it lag behind a lower energy photon on the same journey. This would violate a fundamental tenet of Einstein's relativity, which states that all light in a vacuum travels at the same speed regardless of its energy. Finding such a delay would be direct evidence that the classical picture of spacetime is incomplete. This very idea has driven physicists to use the universe's most violent and distant events as natural laboratories. When a gamma-ray burst explodes billions of light-years away, it sends a blast of photons across a vast spectrum of energies, all heading toward Earth. By meticulously measuring the arrival times of these high-energy and low-energy photons after their epic journey, scientists can hunt for that telltale delay. Even a difference of mere milliseconds could be a smoking gun for quantum foam. Similarly, the incredibly precise detectors used for gravitational waves, like LIGO and Virgo, might one day be sensitive enough to detect a faint background hiss, a stochastic gravitational wave background generated by the frothing activity of spacetime itself at the beginning of the universe. These experiments are pushing the boundaries of our technology, not to look at stars or galaxies, but to feel the very texture of the stage upon which they exist. Ultimately, the concept of quantum foam represents the final frontier of our understanding, the point where our two most successful theories, general relativity and quantum mechanics, meet and clash in a storm of infinite probabilities. It forces us to confront the possibility that space and time are not fundamental, but emergent properties that arise from something deeper, something that operates by rules we have not yet discovered. This isn't just an academic exercise, it is a quest to understand the true nature of reality at its core. Is the universe ultimately granular, a cosmic digital simulation built from discrete bits of spacetime? Or is it something even more bizarre, a fluctuating network of relationships where geometry itself is born from the entanglement of quantum information? The search for quantum foam is our first tentative step into that unknown, an effort to feel the grain of the cosmic wood from which all of existence is carved. But our journey into the cosmos is not just about reaching for the stars, it's also about confronting the challenges we've created in our own celestial backyard. For all our ambitions of interplanetary colonization and deep space exploration, a very practical and urgent problem is developing right above our heads, one that could trap us on Earth and sever our connection to the wider universe. This isn't a distant asteroid threat or a solar flare. It's a crisis of our own making, a silent, high-speed cloud of shrapnel that we've been casually assembling for decades. The danger is known as the Kessler syndrome, a chillingly plausible scenario where the space around our planet becomes so saturated with debris that a single collision could trigger an unstoppable cascade, rendering entire orbital pathways impassable for generations. The concept was first formally proposed by NASA scientist Donald Kessler in 1978, a time when the number of objects in orbit was a fraction of what it is today. His theory was elegantly simple and terrifyingly logical. Imagine a single collision between a defunct satellite and a piece of old rocket debris. That impact wouldn't just create two pieces of junk, it would shatter them into hundreds, if not thousands, of new fragments, each now a high-velocity projectile in its own right. These new fragments significantly increase the probability of further collisions, which in turn create even more debris. This domino effect could theoretically reach a tipping point where the chain reaction becomes self-sustaining, a runaway process that would rapidly pepper low Earth orbit with a dense and ever-expanding cloud of shrapnel. In the worst-case scenario, frequently used orbits could become so hazardous that launching new satellites or crewed missions would be akin to navigating a bullet-filled shooting gallery, with the risks far outweighing the rewards. The nightmare outcome is a permanent barrier, a cage of our own creation that locks humanity on its home planet. This is not a theoretical future threat. We have already witnessed terrifying previews of this cascade in action. On February 10, 2009, a functioning American communications satellite, Iridium-33, collided with a defunct Russian military satellite, Cosmos 2251, over northern Siberia. They were traveling at approximately 26,000 miles per hour relative to each other. The force of the impact was catastrophic, utterly destroying both spacecraft and generating over 2,000 large, trackable pieces of debris, along with an estimated hundreds of thousands of smaller fragments too tiny for our current networks to monitor. This single event increased the total amount of trackable space debris in low Earth orbit by nearly 10% overnight. Each one of those fragments, some as small as a marble, now carries enough kinetic energy to disable or destroy any spacecraft it hits. This cloud of debris will remain a navigational hazard for decades, if not centuries, continuously crossing the paths of other satellites and the International Space Station, which must regularly perform maneuvers to avoid potential impacts. The scale of the problem is already staggering. The United States Space Surveillance Network currently tracks over 27,000 objects larger than a softball orbiting the Earth. But that's just the tip of the iceberg. There are an estimated 500,000 pieces of debris between the size of a marble and a softball, and over 100 million fragments larger than a millimeter. At orbital velocities, even a fleck of paint can chip a spacecraft's window, and a bolt can strike with the force of a hand grenade. This isn't just a problem for astronauts, it threatens the very infrastructure that modern society depends on. Our global telecommunications, weather forecasting, GPS navigation, financial transactions, and even aspects of national security are all enabled by a fragile constellation of satellites flying through this increasingly crowded and dangerous environment. A major cascade event could wipe out critical capabilities, setting technology and global connectivity back by decades. Preventing this debris-filled future is no longer a matter of simple cleanup. It requires a fundamental shift in how we approach space as a shared environment. The first and most crucial step is prevention through better design and responsible practices. This includes designing new satellites to be more maneuverable at the end of their lives, equipped with enough fuel to either push themselves into a graveyard orbit or perform a controlled re-entry into the atmosphere where they will safely burn up. There are also pushes for international agreements mandating that rocket upper stages be deorbited after use instead of being left as massive, tumbling hazards. But prevention alone is not enough for the debris already there. The next frontier is active debris removal, a field that sounds like science fiction but is rapidly becoming a critical engineering pursuit. Concepts are being developed and tested for dedicated space tow trucks or sweeper satellites that could rendezvous with large, defunct objects and remove them. Methods being explored include using robotic arms, harpoons, nets, and even lasers to nudge debris toward the atmosphere. Several companies and space agencies are already building and testing prototype technologies for this very purpose, recognizing that a sustainable future in space depends on our ability to not only add new things but also take the old ones out. The Kessler syndrome ultimately transcends engineering. It is a profound lesson in cosmic responsibility. It forces us to ask what kind of species we want to be as we venture beyond our world. Will we be explorers who treat space with the same short-sighted carelessness we have often shown our own planet, littering our celestial neighborhood with dangerous junk? Or will we learn from our mistakes and become stewards, consciously developing the technologies and international treaties needed to keep the orbital pathways clear and safe for future generations? The silence of the void is not an excuse for negligence. How we manage the space around our world today will determine whether the dream of space exploration remains open for our children, or if we ultimately close the door on ourselves, surrounded by the silent, spinning monuments to our own carelessness. For decades, the Pioneer 10 and 11 spacecraft were celebrated as some of humanity's most successful robotic explorers, the first to journey through the asteroid belt, the first to make close observations of Jupiter and Saturn, and the first set on a course to leave our solar system entirely. But as they sailed into the profound darkness of the outer solar system, a tiny, persistent whisper of a problem began to emerge from their telemetry data. By carefully tracking the precise Doppler shift of their radio signals, navigators at NASA, a jet propulsion laboratory, could measure their velocity with incredible accuracy. And that's when they noticed something was off. Both spacecraft, now millions of miles from the Sun, were experiencing a constant, minuscule, and utterly unexplained acceleration back toward the inner solar system. It was as if a faint, invisible thread was ever so gently tugging them homeward. This deviation was astonishingly small, just about 10 billion times weaker than the gravity we feel on Earth's surface, but it was undeniably there, a stubborn anomaly that refused to go away. Dubbed the Pioneer Anomaly, this tiny drift became one of the most tantalizing puzzles in modern astronomy, a ghost in the machine that defied immediate explanation. The mystery captured the imagination of physicists worldwide because its potential implications were so profound. Could this be the first detectable signature of dark matter exerting a gravitational pull within our own solar system? Or was it evidence that our understanding of gravity itself was incomplete, a hint that Einstein's theory of general relativity needed modification on very large scales, an idea known as modified Newtonian dynamics or MND? Perhaps it was something even stranger, a previously unknown interaction between matter and energy. For nearly 2 decades, the Pioneer Anomaly served as a beacon for those searching for cracks in the standard model of physics, a reminder that sometimes the biggest revelations are hidden in the smallest, most meticulous measurements. It was a classic example of how science often advances not by the loud, expected discoveries, but by the quiet, persistent whispers of data that simply don't fit. The resolution to this decades-long mystery is a masterclass in scientific detective work and a testament to the power of perseverance. A dedicated team of researchers, led by Slava Turyshev, embarked on a monumental effort to crack the case. They faced a formidable challenge. The original engineers who designed the Pioneers had long since retired, and much of the old data was stored on archaic formats like magnetic tapes and even punch cards. The team spent years painstakingly recovering and digitizing this historical data, building a complete thermal model of the two spacecraft from the original engineering blueprints. Their breakthrough came when they realized that the heat generated by the spacecraft's radioactive power sources and their onboard electronics wasn't radiating away from the craft symmetrically. More heat was being emitted from the back of the spacecraft's main dish antenna, which faced toward the sun, than from the front. This created a tiny but constant photon pressure, a gentle push from the spacecraft's own heat, acting like a faint solar sail pushing it backward. This anisotropic thermal radiation provided just enough force to account for the anomalous acceleration perfectly. The ghost was not a new force of nature, but the ghost of engineers past, a subtle design oversight that had waited patiently in the data to be understood. While the solution turned out to be conventional physics rather than a revolution, the legacy of the Pioneer Anomaly is anything but a letdown. It underscores an absolutely critical lesson for all of science: the immense importance of meticulous data archival and the profound value of long-term precision tracking. Without the decades of carefully recorded Doppler data, the anomaly would never have been detected in the first place. This episode has directly influenced the design of all subsequent deep space missions, like New Horizons, which flew by Pluto. Engineers now carefully model the thermal properties of their spacecraft to account for and minimize such effects, ensuring that the data they send back about the gravitational environment of the outer solar system is as clean and unambiguous as possible. The story teaches us that before we can confidently proclaim a discovery of new physics, we must first exhaustively understand our own tools and their subtle, often invisible, influences on the experiment. Ultimately, the tale of the Pioneer Anomaly is a powerful reminder that the universe reveals its secrets in many ways. Sometimes it's through the brilliant flash of a supernova or the dramatic collision of black holes. But other times, it's through the patient, painstaking analysis of an almost imperceptible drift in a tiny probe billions of miles away, a drift that forces us to look closer, think deeper, and question everything we think we know. It proves that there is no such thing as an unimportant mystery in science, and that the relentless pursuit of an answer, even for a problem that turns out to have a mundane explanation, invariably sharpens our tools, deepens our understanding, and prepares us for the next, truly revolutionary anomaly waiting to be found in the data. But what if the great cosmic silence isn't a sign of our solitude or a warning of inevitable doom, but rather a deliberate policy? This is the captivating premise of the zoo hypothesis, a thought experiment that transforms the Fermi paradox from a terrifying question into a profoundly intriguing one. Proposed by radio astronomer John Ball in the 1970s, this idea suggests that advanced extraterrestrial civilizations are not only aware of us, but have chosen to place our planet in a kind of cosmic quarantine. In this scenario, Earth is effectively a designated wilderness area or a safari park within a larger, organized galactic community, and humanity is the unaware wildlife being observed from a respectful distance. The reason we haven't received any visitors or signals is not because they aren't there, but because they are following a strict protocol of non-interference, a prime directive on a universal scale. The motivations behind such a policy are as fascinating as the idea itself. A civilization capable of interstellar travel would almost certainly possess technology so far beyond our own that any interaction, no matter how well-intentioned, could be catastrophically disruptive. They might view us as a fragile, developing culture that needs to be protected from external influence to ensure our organic and authentic evolution. Just as anthropologists studying an uncontacted tribe in the Amazon strive to avoid contamination to preserve its unique culture, a galactic federation might have strict ethical guidelines against interfering with pre-contact societies. Our scientific, social, and technological development could be seen as a priceless natural process, an experiment in consciousness that must be allowed to run its course without spoiling the results. Contact might only be initiated once we reach a specific milestone of maturity, perhaps when we develop the capability for interstellar travel ourselves or achieve a stable global society, proving we are ready to join the cosmic conversation. This hypothesis inevitably leads us to a startling possibility that evidence of extraterrestrial intelligence might not be absent, but deliberately hidden in plain sight. If a civilization is advanced enough to enforce a galaxy-wide quarantine, they are certainly advanced enough to conceal their presence perfectly. Any probes they might have in our solar system could be equipped with stealth technology far beyond our detection capabilities, watching us while remaining utterly invisible. They could be actively filtering their communications, ensuring that no stray signal from their bustling interstellar networks ever leaks into a frequency or direction that our primitive radio telescopes might accidentally pick up. The very void we interpret as silence could be a carefully maintained buffer, a one-way mirror that allows them to observe us while we see nothing but our own reflection. This concept forces a deeply introspective question about humanity's own readiness. If we are being observed, what would the observers see? Would they witness a species on the cusp of enlightenment, showing glimmers of cooperation, scientific curiosity, and environmental stewardship? Or would they see a turbulent, adolescent civilization, still plagued by war, inequality, and the reckless endangerment of its own planet? The zoo hypothesis reframes our search for extraterrestrial intelligence into a mirror held up to our own societal evolution. Our efforts to detect signals like the SETI program could be akin to a zoo animal trying to attract the attention of its keepers, unaware that the keepers are watching all along, waiting for a more meaningful sign of awareness or a change in behavior before they decide to open the gate. While purely speculative, the zoo hypothesis offers a uniquely peaceful and optimistic solution to the Fermi paradox. It exchanges the chilling emptiness of a dead universe or the terrifying prospect of a great filter with a universe that is alive, organized, and perhaps even nurturing. It suggests that the cosmos might not be a hostile wilderness but a managed garden, and that our current isolation is not a prison sentence but a protected period of growth. It adds a layer of profound mystery to every unexplained anomaly in the sky and every silent sweep of a radio telescope, inviting us to wonder not just if we are being watched, but what we must become to finally earn a wave back from the watchers. Now, let's venture into one of the most profound and enduring puzzles in all of theoretical physics, a paradox so deep it strikes at the very heart of our understanding of reality and threatens to unravel the fundamental laws of the universe. This is the black hole information paradox, and it begins with a seemingly simple question with impossibly complex implications. What happens to information when it falls into a black hole? According to the cherished principles of quantum mechanics, information is never truly lost. It might be scrambled, hidden, or transformed into an unrecognizable state, but it must be preserved in some form. This is a foundational pillar of quantum theory, essential for predicting the future state of a system. If you know the complete quantum state of a set of particles, you should, in principle, be able to reverse time and trace them back to their origin. This principle of unitarity ensures the universe is predictable and causal at a quantum level. The paradox was thrust into the spotlight by Stephen Hawking in the 1970s through his stunning work on black hole evaporation. Hawking realized that black holes are not completely black. They emit a faint glow of radiation due to quantum effects near the event horizon. This Hawking radiation is thermal, meaning it is completely random and featureless, carrying no information about what fell into the black hole. As the black hole radiates, it slowly loses mass and eventually evaporates away completely. And here lies the catastrophic problem. If a black hole forms from a specific collection of particles, say, a star made of hydrogen, a spaceship made of iron, and a book containing the complete works of Shakespeare, and then vanishes, leaving behind only generic thermal radiation, then all the specific information about that hydrogen, iron, and Shakespeare has been irretrievably erased from the universe. This violates the core tenet of quantum mechanics, creating a fundamental paradox that pits Einstein's theory of general relativity against quantum theory in a direct and irreconcilable conflict. Hawking himself initially believed that information was indeed lost, a conclusion that sent shockwaves through the physics community. It implied that our most fundamental theories were incomplete, and that at the heart of a black hole, the laws of physics simply broke down. This stance sparked a famous bet between Hawking and fellow physicist John Preskill, who argued that information must somehow be preserved. For decades, this debate raged, representing a schism in our understanding of how the universe operates. The implications are staggering. If information can be destroyed, then the past is not necessarily determined by the present. Causality breaks down, and the universe becomes fundamentally unpredictable. Resolving this paradox isn't just an academic exercise. It is essential for any theory that seeks to unify gravity with quantum mechanics into a single, coherent framework of quantum gravity. One of the most compelling potential solutions emerges from the holographic principle, which we explored earlier. This mind-bending idea suggests that all the information about everything that falls into a black hole is not lost inside its mysterious interior, but is instead encoded on its two-dimensional event horizon. Imagine the event horizon as a vast cosmic hard drive. When an object falls in, it doesn't vanish into a point of infinite density. Instead, its information is smeared and stored across the surface area of the black hole in a vastly scrambled and holographic form. Later, as the black hole evaporates via Hawking radiation, this information is not destroyed but is slowly and chaotically emitted back into the universe through subtle correlations within the radiation itself. The radiation only appears random if you examine individual particles, but if you could collect all of it and decode its incredibly complex patterns, you could, in theory, reconstruct everything that ever fell in. This process would preserve the information, but in a way that is practically impossible to recover. Much like burning a book releases smoke and ash, the information of the book is technically still in the universe, but scattered into a form that is irrecoverably lost to any practical observer. Recent advances, particularly in string theory, have provided tantalizing mathematical evidence that information is indeed preserved. Through sophisticated calculations of how black holes behave in various hypothetical universes, string theorists have shown that the process of black hole formation and evaporation can be made consistent with quantum mechanics, suggesting information is not lost. However, the precise mechanism for how the information gets from the collapsing star onto the horizon and then back out in the radiation remains one of the most active and fiery areas of research in theoretical physics. The answer likely requires a full theory of quantum gravity, which would describe the precise microscopic structure of spacetime at the Planck scale and reveal the true nature of the black hole singularity. Resolving the information paradox is not just about saving information. It is about discovering the underlying rules that govern the most extreme environments in the cosmos, rules that apply to the birth of our universe as much as to the death of a star. Yet for all our grand theories about black holes and cosmic origins, we are forced to confront a concept so fundamental it often escapes our notice, the very idea of nothingness itself. We all have an intuitive understanding of nothing. It's the empty space in a box, the silence between sounds, the void we imagine beyond the stars. But this classical notion of a pure, sterile void is perhaps the greatest illusion of all. Modern physics has completely upended this idea, revealing that what we perceive as nothing is in fact a seething, bubbling cauldron of activity, a dynamic arena where particles flicker in and out of existence in a relentless quantum dance. This isn't just empty space, it's the quantum vacuum, and it is anything but empty. This bizarre behavior is a direct and stunning consequence of Werner Heisenberg's famous uncertainty principle, a cornerstone of quantum mechanics that states you can never know both the exact energy of a system and the exact time you're measuring it. On the very smallest scales and over the very shortest time spans, this allows for a monumental loophole in the conservation of energy. The universe can, in effect, take out an energy loan as long as it pays it back almost instantly. This permits the spontaneous and temporary creation of particle-antiparticle pairs from the sheer energy of the vacuum itself. These are called virtual particles, and they are not just a mathematical trick. Their effects are measurable and real. They flash into existence for an unimaginably brief moment, borrowing energy from the future before annihilating each other and vanishing back into the void, returning the energy and leaving no trace. This endless cycle of creation and destruction is happening everywhere, all the time, in the space between the stars, in the air between the atoms of your own body, in the deepest, darkest voids of intergalactic space. The vacuum is alive with this ephemeral quantum foam. We can actually witness the tangible effects of this quantum frenzy in a laboratory. The most famous demonstration is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948. Imagine placing two perfectly smooth, uncharged metal plates extremely close together in a vacuum, separated by a gap smaller than the width of a human hair. Outside the plates, a whole spectrum of virtual particles of all different wavelengths can pop in and out of existence. But in the narrow gap between the plates, only virtual particles with wavelengths that fit perfectly between them can appear. This creates a profound imbalance in the quantum pressure, with more virtual particles pushing on the outside of the plates than on the inside. The plates experience a faint but measurable force pushing them together. This astonishing effect, first measured definitively in 1997, is a direct experimental confirmation that empty space is not passive. The void itself exerts a force, proving that nothingness is a misnomer. This leads us to one of the most embarrassing and profound problems in all of theoretical physics, a problem so severe it's often called the worst prediction in the history of science, the cosmological constant problem. When physicists attempt to calculate how much energy this endless creation and annihilation of virtual particles should contribute to the vacuum of space, they use the well-established rules of quantum field theory. They add up the contributions from all possible fields and all possible energy levels. The result is a number so catastrophically large it is almost incomprehensible. The calculated vacuum energy density should be around 120 orders of magnitude. That's a 1 with 120 zeros after it, greater than the value we actually observe from astronomical measurements. This discrepancy is not a small rounding error. It is larger than the difference between the size of a single proton and the entire observable universe. If the theoretical calculation were correct, the repulsive force of this vacuum energy would have been so immense that it would have ripped apart every atom, every nucleus, in the infant universe before stars or galaxies could ever have formed. The fact that we exist at all is proof that this calculation is wildly, inexplicably wrong. This problem is not just an academic curiosity. It sits at the very heart of one of the greatest mysteries in cosmology, the nature of dark energy. The observed acceleration of the universe's expansion, which we attribute to dark energy, requires a very specific, very small amount of energy density to be infused throughout the vacuum of space. This measured value is exactly in line with the value we get from astronomical observations, but it is a tiny, tiny fraction of the enormous value predicted by quantum field theory. So the puzzle is twofold. Why is the vacuum energy so small? And why does the small amount that remains have exactly the right value to cause the acceleration we see? It suggests that somehow the frenetic activity of the quantum vacuum almost completely cancels itself out, leaving behind only the faintest whisper of energy that we call dark energy. Understanding this cancellation mechanism would unlock the secrets of dark energy and the ultimate fate of the cosmos. This brings us to a deeply philosophical and speculative frontier explored by physicists like Lawrence Krauss, who ask a staggering question: could the entire universe have emerged from nothing? Krauss and others argue that if the quantum vacuum is unstable and capable of spontaneous fluctuation, then the transition from nothing to something might not require a supernatural cause. In this view, the nothing they refer to is not a pure philosophical void, but the quantum vacuum itself, a realm devoid of matter and radiation but still governed by the laws of quantum physics. They propose that our cosmos could be the result of a massive, spontaneous quantum fluctuation in a pre-existing primordial vacuum, a bubble of space-time that inflated into the universe we see today. In this scenario, the total energy of the universe might actually be zero, with the positive energy of all the matter and radiation perfectly balanced by the negative gravitational energy of their attraction, meaning it could have come from nothing without violating the conservation of energy. This idea is, of course, fiercely debated. Philosophers and some physicists argue that this simply redefines nothing to mean something. A quantum vacuum with laws and potentialities is not true nothingness in the absolute philosophical sense. True nothingness would entail the absence of space, time, and physical laws themselves, a concept that is arguably beyond the reach of scientific inquiry. The debate highlights the complex intersection of physics and metaphysics, where our scientific definitions of concepts like nothing and something bump up against centuries of philosophical thought. It forces us to question whether a universe can truly create itself from scratch, or if it always requires some form of pre-existing framework, even if that framework is an empty, law-filled void. Ultimately, the mystery of the quantum vacuum represents a fundamental clash between our two most successful theories, quantum mechanics and general relativity. Quantum field theory gives us a prediction for what the energy of empty space should be, and general relativity tells us how that energy should gravitate and influence the expansion of the universe. The fact that these two answers are irreconcilably different is the clearest possible signal that we are missing a deeper theory, a theory of quantum gravity that can seamlessly unite the world of the very small with the geometry of the very large. The hum of the quantum vacuum is a constant reminder that nothing is ever truly still, and that the greatest secrets of the cosmos are hidden not in the distant stars, but in the seemingly quiet void right in front of us, challenging us to redefine nothingness itself. As we bring this exploration to a close, it's worth pausing to reflect on the extraordinary journey we've just taken together, a voyage that has stretched from the first fraction of a second after the Big Bang to the farthest theoretical edges of the multiverse. We felt the subtle ripples of colliding black holes as they warped the very fabric of spacetime, a phenomenon that has given us an entirely new sense with which to perceive the cosmos. We've confronted the haunting presence of dark energy, an invisible force silently pushing the universe apart at an ever-increasing rate, dictating a future that could end in icy isolation or catastrophic rupture. We've peered into the abyss of a black hole's event horizon and grappled with the paradox of information seemingly vanishing from reality, a puzzle that forces us to question the most fundamental laws of physics. Each of these discoveries does more than just add a new piece to our cosmic model. It fundamentally reshapes our understanding of reality itself. They reveal a universe that is far stranger, more dynamic, and more wonderfully bizarre than we could have ever imagined just a century ago. This expanding knowledge is profoundly humbling. It reminds us that for all our intellectual achievements, we are still nascent explorers in a cosmos that guards its deepest secrets closely. Our most brilliant theories are not final answers, but rather waypoints in an ongoing quest, stepping stones that allow us to reach for the next greater question. This is the beautiful, endless cycle of science. Every answer unravels into a dozen new mysteries, each more compelling than the last. The true value of this journey lies not just in the facts we've gathered, but in the perspective it offers. It connects us to a story much larger than our daily lives, a cosmic narrative written in the language of gravity, light, and quantum mechanics. It invites us to see ourselves not as separate from the universe, but as an active, conscious part of its unfolding, a way for the cosmos to know itself. This perspective can be a source of immense wonder and inspiration, a reminder that the same physical processes that forged galaxies and stars also assembled the atoms that make up our bodies. We are, in the most literal sense, stardust contemplating the stars. I'd love to hear which of these cosmic mysteries captured your imagination most powerfully. Was it the holographic principle's suggestion that our reality might be a projection, the spine-tingling possibility of wormholes bridging distant regions of spacetime, or the haunting silence that gives rise to the Fermi paradox? Share your thoughts in the comments below. Let's continue this conversation and learn from each other's curiosity. If you've enjoyed this deep dive into the frontiers of physics, make sure to subscribe and hit the notification bell so you don't miss our next exploration into the universe's secrets. Thank you for joining me on this incredible journey through the chronicles of the universe. Until our next adventure, stay curious and never stop looking up in wonder.